Professor at the University of Wisconsin Stout. He has a PhD in materials engineering and has worked as a researcher and professor at various universities and institutions. He has authored and edited several books and has published numerous research papers. He is also the editor-in-chief of the Journal of Materials Engineering and Performance.
Hi.
I request Sir to share his valuable experience.
Okay, hello, thank you. Good evening. Well, good morning for you, actually, I suppose, for most of you. It's 11 p.m. here.
Hello. Hi.
Yeah. Hi. Can you hear me?
Okay. Okay. One second. Okay.
All right.
Okay.
Well,
no problem. Yeah. No problem.
all right.
Now this another
So-
speaker, he has to mute. Hi. Okay, now it's
All right. So, well, let me just first thank the people here. I want to thank the Institute Director, Professor Chattopadhyay, HOD Professor Kumar, and organizing committee, especially Professor Singh, with whom I had correspondence. I was not aware of the conference until I spoke to Professor Malay Banerjee of Jaipur a month ago, and he mentioned about it. So after that, I got in touch with Professor Singh, and that's how I'm here. So very happy to be here. Looking at the session schedule, it looks like we have 5 speakers in this session. So in 90 minutes, so I'm looking at about 15 to 18 minutes of my presentation. If I go overboard, please someone interrupt me and stop me. So anyhow, I'm going to talk about some basic issues that have fascinated me in liquid phase processing of materials. And we are looking at areas like traditional melting and casting, mold metal reactions, and electrode metal reactions, crucible melt reactions. In ceramic metal composites, we are concerned with the wettability, reactivity, and interfaces between fibers and the metal matrices or between particles and the metal matrices. For the last several decades, my interest has been in joining of ceramics and metals. So we had been receiving funding for certain application areas. For example, demonstrate diffusion bonding and brazing for leading edge components in some vehicles, mainly zirconium diboride based composites, or fuel injector systems where we have to join a tube, fuel carrying tube like Kovar tube to silicon carbide. Some heat exchanger systems where titanium tubes carrying a fluid are to be bonded to high conductivity carbon-carbon composite and carbon foam. Solid oxide fuel cells where we were working with YSZ, zirconia stabilized, deuterium stabilized zirconia and steel. And then some gas turbine engine components. So those were the application areas, but in all these different fields, the interaction between liquids and solids are critical. So fundamentally, we know that we have reactions and infiltration and adhesion kind of problems in liquid solid systems. We also have issues of residual stresses because of thermoelastic incompatibility between bonded materials. So we have several different methods to overcome those issues. My focus today is more on the fundamental side, wettability and reactivity side. There is a lot of literature data from the 1930s onwards in Ukraine and Russia and other countries. A lot of work was done on wettability at high temperatures. But the problem is that the data are all over the place. Here is an example of literature data on aluminum-alumina system. If you look at the contact angle versus temperature, the numbers are all over the place. You cannot really make sense out of it. And part of the reason is that there are no standardized test methods for characterizing interfaces and wettability. And another reason is that contact angles are extremely sensitive to testing conditions. So effectively, you can actually use contact angle measurements to probe the surface and interface. And we know the contact angle is basically the angle that you see between the liquid and the solid through the liquid region here. So unlike low temperature systems where there is hardly any reaction other than absorption on the surface, high temperature systems show very complex phenomena. So here are some examples that we have been looking at. Aluminum on carbon. You form aluminum carbide by exothermic reaction, and the carbide crystals actually are ahead of the liquid. So the liquid is actually spreading on a modified surface. In other systems, like on magnesium oxide, when you have nickel aluminum, there is reaction and whisker formation. Anisotropy also occurs when you have inhomogeneous surface. For example, when you have a composite surface and you're trying to measure wettability of another metal on the composite, the spreading is not isotropic. We also have other issues that we have seen. For example, evaporation and condensation, and all of this is done under very high vacuum. So here is an example of a nickel droplet that was in contact with a single crystal alumina with chromium PVD layer. And what we see here is that even before the droplet can spread completely, there is evaporation and condensation of nickel and formation of different zones of nickel chromium eutectic. So the droplet is actually spreading on a modified surface. Another thing we see is cracking because of expansion mismatch between the liquid and the solid. The classic example is aluminum in contact with silica. And that reaction gives the volumetric expansion and the cracking. So essentially, when you have the liquid droplet to measure the contact angle, the liquid is actually penetrating, and the angle that you measure is incorrect. So all of those issues are very difficult to actually experiment with. So we have been interacting with a group from Poland with Dr. Natalia Sobczak. She is currently the vice president of a Polish Academy of Sciences. And she has this high temperature wettability test unit, arguably the most sophisticated unit in the world, as far as I know. This can really manipulate the droplet under high vacuum. And you have many other features that you can use. So we have been working with this machine jointly and wanted to show you some video clippings here of liquid metal spreading on solids. Now this is just a 2 or 3 millimeter diameter droplet that is spreading on the solid surface here. We know that little droplets have oxide skin. So here looking at aluminum silicon on an alumina substrate with nickel phosphorus coating, look at what happens to oxide layer here. You will see that the oxide is really tenacious and the liquid is actually beginning to seep under it. So essentially the oxide forms a cap and liquid begins to spread underneath. And this is just a very small droplet, 2 or 3 millimeters in size under really high vacuum at high temperatures. So these are the kind of issues that complicate measurements of wettability in many systems. So how do you actually examine these things? Well, let's look at another example here. You're looking at how at high temperature the oxide will actually disintegrate. You can see the little particles of oxide broke off and you have a cleaner surface here. And this is because not just because of high vacuum, even under this vacuum you will have an oxide skin, but the temperature was increased above 1000 Celsius. So there was oxide dissociation. So how do you handle some of these problems? Well, Dr. Sobczak has this special instrument where she's able to squeeze the little droplet on the substrate. In the normal cell-side drop test, the solid is first brought in contact with the solid substrate and they are heated in contact. But the problem here is that you have no control on the time because interactions will begin right in the solid state itself. So if you want to study the liquid-solid reaction, this is not a correct approach. So what is done here is the solid metal and substrate are independently heated and at some time they're brought in contact. So this kind of a test allows more scientific approach to wettability study. So you're looking at a droplet that was squeezed out under high vacuum, and because of the squeezing action, the oxide on the surface was removed. And when you look at the contact angle data, even at low temperature at 973 Kelvin, you're able to get the same low contact angle that you would have obtained at much higher temperature with contact heating. So what it shows is that a lot of things are happening at high temperature that we cannot really understand by applying the low temperature framework of wettability. And this is just showing you the same thing, but we are looking at the bond strength after measuring the contact angle. So we let the droplet solidify, then we bisect the droplet and do a shear test to measure the shear strength. So what we have seen is that when you remove the oxide on the surface of the droplet, the bond strength really goes up, even at relatively low temperatures, as compared to if you had contact heating. One of the things we have been able to do is to push liquid droplets on the surface. So this is actually nickel tungsten on magnesium oxide, not magnesium, but magnesium oxide. And under high vacuum, you are able to push the droplet and open up this interface after a fixed amount of time. And after cooling, you can actually look at the interface and see what kind of reaction it occurred. So something interesting we see, after the droplet is pushed out, the little droplet that was 2 to 3 millimeters in diameter that breaks up into micron-sized droplets underneath. And those little droplets, they get captured into these kind of dislocation edge pits, really teeny edge pits. So we are actually looking down from the top on the surface that was cleaned up by pushing the droplet after a fixed amount of time. Generally, we believe that you need high bond strength, you need good wettability for high bonding, but that's not always the case. You can see here that this little ceramic plate gets bonded even though the contact angle measured was pretty high. Other thing that we have been able to do is to put the drop suction approach, or we can actually rotate the substrate and see the effect of shearing on interface formation. So when we do the suction thing, after a fixed amount of time, the droplet is pulled out and we are able to open up the surface here underneath. And this sample can be transferred right from the tester into a vacuum to the X-ray photoelectron spectroscopy system. So it doesn't expose to atmosphere. Here you're looking at the reaction, real-time reaction between aluminum and silica. So this is the silica plate, and you're looking and seeing the reaction layer forming through the transparent silica substrate. And you can actually study in situ the interactions that are taking place. The same thing, you're looking at several silica plates through which liquid aluminum is actually permeating and also reacting. So the liquid is moving, the reaction layer is forming. So you can actually see the kinetics of spreading and the kinetics of reaction from this kind of a system. So a lot of things are happening that we don't see without use of this kind of instrument here. Another example is wetting and de-wetting kind of a thing. So under high vacuum, this little droplet, when it melts, there is some reaction taking place and teeny bubbles can form underneath. And you will see the bubble jump up and down because of the bubbles escaping. You will see that in a few seconds. This is what is happening now. Now the time is actually almost 30 minutes, but we have high-speed videos here. So there are a lot of effects that are taking place. You can actually see this is actually aluminum drop in contact with this magnesium spinel here. And when you heat it, you can see the bonding here. When you cool, the plate is actually lifted up because the bonding is very good here. Another thing we see is the actual real-time change in the volume. You see right now the surface is flat, horizontal, but with reaction, it is changing. It is becoming more curvy because of the reaction and volumetric change. You can see the surface of the substrate becoming more curved. And that is what is going to cause the contact angle measurements to be in error. So lot of these things are happening, and we have been looking at some of these features, but I don't want to take too much time. It's already almost 11:30 here. So in summary, we are able to conduct some special tests that are not possible in conventional sessile drop test, and we are able to observe some unusual phenomena. So I want to thank my colleagues, Professor Natalia Sobczak from Poland. We have been collaborating for almost 30 years, off and on. Dr. Mrityunjay Singh and Mike Halbig from NASA. I've been working with them almost for 25 years, off and on, so a lot of funding was received from them. I just want to wrap up with one last slide, and I want to mention about the journal. We have this Journal of Materials Engineering and Performance that is published by Springer for the American Society for Materials. Some of you, I'm sure, are familiar with that journal. So we have quite a few issues each year. We get over 5,000 submissions each year, and we are able to publish about 1,000 papers in 24 issues. The numbers are going up. Now, we would like to accommodate as many papers as we can, but the challenge is that we have some limitations in terms of how many we can publish. So even though we don't have any fixed rejection rate, we have to decline almost 67% paper that are submitted. Not because they're bad necessarily, but because we cannot accommodate many papers. So this is an important journal. This is a flagship journal of ASM. This is solely owned by ASM. There are 3 other journals that ASM owns jointly with TMS, Medtrans A, B, and then International Materials Reviews. But JMAP is solely owned by ASM. So just wanted to show you this slide that we are getting good visibility. We had over 1 million downloads. Impact factor is also going up slowly. A lot of our readers are not publishing papers. They are industry professionals. So they read papers, but they don't necessarily publish and cite. So our citation numbers are not that high, but they're reasonably good. So this slide is just to encourage you to consider submitting your work to JMAP, original papers or comprehensive review papers. And if you have any ideas about guest editing special issues, you can get in touch with me. So with that, I would conclude and say thank you to you. If anyone has any comments or questions, I'll be available to answer. Thank you again.
Yeah, thank you, sir. So that Professor Asthana has given a good insight on the wettability of particles, and so this is equipment you cannot find anywhere that you have got. So wettability measurement, very precise measurement, how these droplets are contacting, and this great study. And we hope from this conference also we'll send some selected papers for publishing in this International Journal of Materials Engineering and Processes. And I request anybody have any questions? Yeah. So this I want to know just only, but this droplets like wettability problem is always in there in composite makings or in particles. Whether it is properly that wetting, it is not that, then it is not make a coherence bond in that. So what are the way you can improve the wettability of any particle when you are making a composite in that?
So people have been, looking at many different things, starting with, I think, the 1970s or even earlier. Subrat Ray and P.K. Rohatgi at Kanpur IIT way back, they were experimenting with adding magnesium to aluminum. Magnesium, being a surface active element, is able to modify the surface and interface between the solid and the liquid. So magnesium is well known active agent for composites. People have used different kinds of surface coatings on particulates, electroless coatings of nickel, copper, and other materials. And if you have a nickel coated or copper coated particle, they will disperse relatively easily compared to uncoated particles. You have to also make sure to preheat the powders or fibers, or remove any sizing on fibers before you bring them in contact with the liquid. So preheating is important. And of course, sometimes preheating can change the surface structure. We have seen that if you have graphite particles and if you preheat them, the surface gets modified, more porous. So, but anyway, so those are some methods people have used to make composites and improve wettability. Those are practical approaches.
Yes, sir. Thank you, sir. So I am Dr. KKC. That we have a many mail we have discussed in that for regarding that, and Professor Amitesh was in contact with you for that getting in that in conference. So thanks for it is a valuable presentation, and our students are also there here, so they are able to know that how does wettability affect in the processing also. So thank you very much, sir. So we'll be in touch, and we'll probably send some papers for that publishing as per your guidelines.
Certainly.
And
Okay.
this. Yeah. Thank you, sir.
All right. Well, thank you very much. And it was good to see everyone. Wish you success with the conference. Thanks again.
Thanks, sir. Thanks, sir. Yeah, next his presentation, online presentation, you can.
Hello.
Dr. Tian Yi Han received his bachelor's degree in mechanical engineering from Xi'an Jiaotong University, China in 2016, and his PhD degree in mechanical engineering from Tsinghua University, China in 2021. Also, he was a joint PhD student at University of Montreal, Canada from November 2019 to August 2020. From March 2022 to March 2024, he was a postdoctor in the State Key Laboratory of Tribology at Tsinghua University. He is currently an assistant professor at Tsinghua University, China.
Hello.
His research interests include liquid superlubricity, hydration lubrication, intermolecular and surface forces. I request Sir to say his valuable expression.
So,
Hello. Can anyone hear me?
yeah, we are properly hearing you, and your video
Okay,
is also
thanks.
good. You seeing your
Okay,
face
thanks.
also.
Thanks everyone, and I'm Tian Yihan from Tsinghua University, China, and it's big thanks to Dr. Sudesh who invites me to make a presentation here. I know maybe my research is about lubrication, and maybe lubrication is not a good idea in this foundry and forming technology, but I hope that our research from science to technology and to application, and this research progress could give you new thoughts during your research. And I also want to explain that I have two. There are two Tianyi here. One with camera and the other one without camera. Because I use my computer to make this presentation, but there's no camera here, so I use a laptop to show the camera. Yeah. So now let's begin. So first, let me share my screen. Hello, everyone. I'm Tian Yihan. Yeah, and today I will introduce the hydrogen lubrication, and this research is mainly carried out in Professor Chen Huizhang and Professor Jianming Luo's group. First, before my introduction, I will first give a brief introduce of the hydration effect and hydration lubrication. First, let's see the one of the most simple molecular in the world, water. As we all know, the water molecular is a polar molecular. That means the average electron density around the oxygen atom is about 10 times larger than that around hydrogen atoms for a water molecular. And this dipole moment of water molecular is about 1.85 D. And then for a water molecular, one water molecular can form 4 hydrogen bonds with the other 4 water moleculars. And the hydrogen bonds length is about 0.176 nanometer. And then I want to introduce the strength of this hydrogen bond compared with the chemical bond between the oxygen and the hydrogen. This hydrogen bond is weaker than this chemical bond, but compared with van der Waals interaction, this hydrogen bond is a little stronger than this van der Waals interaction. So this is just a brief introduction of the water molecular. And then because of the polarity, the water moleculars can be attracted by ions or polar moleculars. Such phenomena is called hydration effect. And for example, like iron hydration and sugar hydration, here protein hydration. And then after that, when a charged surface immersed in salt solution, what will happen? The charged surface can absorb hydrated counter ions to form the stain layer and the diffusion layer. And then after that, when two surfaces approach each other to the distance less than 5 dBi length, and this dBi length is used to describe the length of the diffusion layer. And then if in this case, we can find a repulsion force, and this is called the electric double layer repulsion. And then if the distance decreases to less than 3 nanometer, another strong repulsion can be found, and this is called the hydration repulsion or the hydration force. Due to this strong hydration repulsion between two charged surfaces, in this literature, this is conducted by Professor Jacob Klein's group, and they measured the repulsive force between two mica surfaces. Here, this is two mica surfaces, and the mica is glued on the silica lens. And then what they found? They found that a strong repulsive pressure as high as 10 megapascal, if the distance between two mica surfaces is very low, usually below 3 nanometer or below 1 nanometer. And then they slide the two mica surfaces and found the friction is very low. This is the friction result. Here, this is the friction force, and the x-axis is the normal load. And we can find the friction coefficient. The friction coefficient is the slope of the friction force and the normal load. The friction coefficient is as low as 10 to the power of minus 4 between the two mica surfaces. And this is a very low friction coefficient. And they attributed the superlunar friction to the weak shearing plane. And this phenomenon is called hydration lubrication. And next, in the cooperation work between our group and Professor Xavier's group, Professor Xavier Banqui is a professor of University of Montreal, Canada. And we also found that the strong hydration repulsion occurred in trivalent cations. This trivalent cations we used is a lanthanum content. And also we got a very low friction coefficient during sliding, and the friction coefficient can be as low as 10 to the power of minus 4 and sometimes minus 3. and sometimes -2, but all these are a very low friction coefficient. So these works by Professor J. Klein's group and our groups all suggest that maybe we can get super low friction by the hydration effect for the macro scale contact, because all this previous research is using a SFA setup. The contact is very small, and we call it just a macro scale contact. So how to use this hydration lubrication at a macro scale contact? Then I will introduce how we get super lubricity at a macro scale contact based on hydration lubrication. First, as shown in this figure, for the rough surfaces during sliding, the friction comes from two parts. First is the shear resistance between the contacted asperities, and the second is the shear resistance of the liquid film, as shown here. And the force between the asperities is much larger than that of the shear resistance of the liquid film. So the key for achieve low friction is reducing the shear resistance between the asperities. Then we proposed a method to form a hydration layer on the asperities surface, and this hydration layer can separate the asperities by the hydration effect, by the hydration repulsion. Then the shear resistance should be reduced greatly. So first we make a calculation, and we should prove whether it is possible to separate the asperities by hydration effect. We introduced the surface force into the mixed lubrication model, and the surface force consists of van der Waals force, the electric double layer force, and the hydration repulsion. And I want to emphasize that the key is the hydration repulsion, because it is a very strong repulsion. And then from this we can calculate how many contact pressures can be supported by the hydration force. Let's see what happened. Let's see the results. First, for the surface with roughness of 6 nanometer, as the surface potential increases, the bearing ratio of the hydration force also increases. And when the surface potential is -25, the hydration effect can bear over 60% of the applied load. And then if we fix the surface potential of -20, the bearing ratio of the hydration force increase with the decrease of the surface roughness, and the maximum is over 80% if the roughness decreased to 2 nanometer. So from the calculation, we know it is possible to decrease the friction by hydration effect especially in the mixed lubrication region, because the surface force can support most part of the applied load. So from the calculation, we know if we want to get super lubricity, there are 3 key factors. We need to be satisfy these 3 factors. First, the surface should be very smooth, and the roughness should be in the scale of nanometer. And second is the surface should be charged in water, and negatively charged surface is better. And third is we need strongly hydrated ions in the water, because we need this hydration layer. Then we did the test with a bore on disc tribometer, and the bore is here a silicon nitride bore, and the disc is a sapphire disc. At the beginning, we run the test with acid solution. We can find the friction coefficient decreases rapidly. After the running-in period, we removed the acid solution and used potassium chloride solution as the lubricant. And then we find the super low friction coefficient of 0.005 was obtained. And here the contact pressure is about 250 megapascal, a very large contact pressure. And then we tried different salt solutions and found for the contains with strong hydrogen effect, like the lithium contains, sodium contains, and potassium contains, we can obtain a super low friction. But for the content with weaker hydrogen effect, the friction coefficient is relatively high. By the TEM observation, we found a tribal-induced silica layer was generated on the surface of the silicon nitride ball during the Ronier period, and this silica layer can increase the surface charge density by more than 50%, which can make the surface absorb more hydrated ions and thus enhance hydrogen lubrication. And then we can modify the surface potential by changing the pH value of the solution. We see as the pH value larger than 5. In this region, the surfaces are negatively charged, and we can obtain a super low friction coefficient. But if the pH value decreased less than 4, the surfaces became positively charged, and then the friction coefficient increased. And after that, we want to know whether the hydrodynamic effect can contribute to the superlubricity. The hydrodynamic effect means between the two surfaces, there's a thick liquid film, and this liquid film can separate the two surfaces. And we also do the test at different velocities. We got the curves like this, and as the velocity is high, even for pure water, the super low friction coefficient can be obtained. As the speed decreased to less than 200 millimeter per second, the friction coefficient increased with decrease of the velocity. And then we calculated the film thickness at different velocity. And when the velocity is about 100 millimeter per second, the film thickness is about 1 nanometer. But the surface roughness of the silicon nitride ball is about 5 nanometer. So that means in this case, the lubrication region is a boundary lubrication or mixed lubrication. That means the surface asperities will contact with each other. So we believe that the hydrogen effect and the hydrodynamic effect both contribute to the super low friction in our experiments. The difference is at a lower velocity, the hydrogen effect is dominant. Well, in the case of higher velocity, the hydrodynamic effect becomes dominant. Then, according to the Hofmeister series, this is the Hofmeister series, we know that the divalent and the trivalent compounds have stronger hydrogen effect than the monovalent compounds. So we do the test using divalent and trivalent compounds, and we all found that all these divalent and trivalent compounds can obtain a very low friction coefficient, and the contact pressure is also very high, about 270 megapascal. The interesting thing is that for trivalent compounds, the super low friction coefficient can also be obtained at a very low sliding speed. A low sliding speed means almost no liquid film between the surfaces. Only the hydrogen layers consist of the hydrogen compounds support the applied load. So the trivalent compounds shows the best superlubricity performance. Then we can conclude that the stronger the hydrogen strength, the better the lubrication performance. Next, based on the scientific research, next I will introduce the application of the hydrogen lubrication based on this scientific research. In the previous test, we used the sapphire, silicon nitride, or the mica, and we can find that these materials are all negatively charged. But for some materials, such as PEEK or epoxy resin, their surface is less charged in water at very low surface potential. So if in order to enhance the hydrogen effect, we need to increase the surface potential of these materials. If we can modify the material by grafting some groups, some charged groups or polymer brushes on the surface, such groups or brushes will negatively charge in water. Then we can get a surface with strong hydrogen effect. And let's see what happened based on this concept. We modified the PEEK powder by grafting the sodium sulfonate group. This is the sodium sulfonate group. And then we centrate the modified pig powder into disc for trouble tester. And we can see this is the final modified pig disc. And if we put this modified pig in water, we can expect the surface will release the sodium ions here and become negatively charged. Let's see what happened. First, we analyzed the modified pig by XPS and found this sulfur element peak from sulfonate in this spectrum. That means the sodium sulfonate groups were grafted on the pig powder. And then we also measured the vit potential of the surface for the modified pig, the blue and the green one. The vit potential decreased compared with the red and the black one. These are unmodified one. So that means for the there are more negatively charged sites on the surface in water after modification. Then we measured the friction coefficient and the wear rate. We do tests with sodium chloride solution with concentration of 0.9%. And for the unmodified pig, the friction coefficient is larger than 0.06 at a different velocity. But after modification, the friction coefficient decreased to less than 0.02. And we also found the wear resistance of modified pig, the blue one, is much better than that of unmodified one, and also better than the commercial materials. And then finally, we fabricated the journal bearings with the sulfonated modified pig and tested it by the journal bearing test machine. And during the test, the bearing was lubricated by salt solution, and we can find the friction coefficient decreased to less than 0.01 during our test. And after the test, we can find there almost no wear on the surface. And in other words, the wear of the bearing is quite small. So this is a very good material to make the journal bearings. Then let's go to the summary. The first, the hydrogen effect can be employed in macroscale contact, and the superlubricity can be achieved in mixed lubrication regime. And second, the surface roughness, surface potential in water, and strongly hydrated contents are the key factors for achieving superlubricity at macroscale conditions. And third, the hydrogen lubrication can be employed in some cases, such as water lubricating bearings, artificial joint by the negatively charged modified materials. And this is our group. This is Professor Chen Huizhang, and this is mine. And this is Dr. Sudesh. And thanks to Dr. Sudesh again to invite me to make this presentation. And thanks for your attention and welcome questions.
Thank you, sir. Good presentation on lubrication, how to improve the lubrication. Any question from audience? Otherwise, we can move to the next session because we are going late. We have started late also. And so thank you, sir. If any have questions, then you will contact to you by mail also. Okay. Thank you very much, sir.
Sorry.
Okay. So next presentation is join rakho. He can.
Sorry, any questions?
Presently, that is, they can discuss with you because we are liking time, and we have other two presentation. Next session is very tight schedule, so you can have. They will contact you by. We have circulated a mail. They can correct. So now we have the presentation from our own director here, and just tell about that.
Okay, see you.
Professor Dr. Parthopratim Chattopadhyay has been the director of NIAMT since February 2015. He is a highly respected academician and researcher with a significant contribution to the field of material science and engineering. His leadership at NIAMT has been instrumental in the institute's growth and development. Sure, sir. I would like to request our session chairperson, Professor Dr. Kamlesh Kumar Singh, to please welcome our Honorable Director, sir, with a flower bouquet as a symbol of respect.
Forward, backward pointer. Yep. Thank you, sir. So this is where you become Ghadwala Bahadwala. Okay. Thank you, sir. Thank you, Chairman, sir. My dear colleagues, students, participants. In fact, as the title says, it is not actually some specific science which you have gone through so far. Rather, you may consider it as kind of story or popular lecture where I have tried to cover a span of time ranging about 6,000 years. So it is ocean in a cup of tea. And the aim was to track how the practice, science and technology of solidification evolved over time, what were the driving forces for that, and how it has taken different turn at different juncture. बाबू ये तो हो नहीं रहा है. Okay, I will adapt. It will take time. So actually, our ancestors inherited the process of melting and casting copper sometime around 5000 BC, and it evolved particularly in two regions of the globe. One in old Europe, particularly in the region of Donau Valley, and other where Near East they call it. Basically, it is the region of Mesopotamia, Anatolia, today Iraq, Turkey, like that. So here they started casting of copper using lost works process in the region of old Europe, and this was followed by the casting of bronze in the region of Mesopotamia and Anatolia. The difference is that the archaeological evidences which people gathered from this region are mostly tools, axe, hammers, shovels, like that. The motivation was this region was very rich in copper and gold resources, and their motivation was basically mining. So they focused on manufacturing tool. But in this region, most of the castings which the archaeologists have come across are aesthetic in nature, basically art casting. And for art casting, pure copper was not much useful because it needs fluidity. When you produce a particular art or shape, you need the liquid metal to flow at the intricate corners, and it needs fluidity, it needs a good luster. So they learned to alloy copper with different elements like tin, antimony. And that's how era of bronze evolved. And these are few evidences or testimony of the elegance of art of casting. Recently, a group of researchers identified that an amulet was cast in Mehergarh. So far, people were highlighting these regions as a place of birth of casting technology or solidification technology. But recently, people have identified that this practice was very popular in Mehergarh. And this paper is published in Nature. This is an amulet. This is basically a copper alloy, and they have elegantly investigated the microstructure where they have shown that it is copper dendrite with copper and copper oxide eutectic. The Iron Age started around 1200 BC in China. And these are the elegant example of the art of casting iron, which is there, some statues which are there in the front of Den Fong temple. So, in ancient time, there were two trends. One, producing reproducible casting with utility value. When you cast an axe on hammer, it has to be reproducible in terms of shape and property. And the other trend was unique casting skill with aesthetic value. Reproducibility was not mandate, but aesthetic value, that is surface lustre, reproduction of the desired shape was important. So that's how it started. A good span of time, it was people who are engaged in basically these kind of casting, but there was no commercial value of it. There was utility value, aesthetic value. The commercial value started with casting type metal. Johannes Gutenberg in England, he developed portable printing machine, and it required founding types, letters, and he used lead-tin eutectic. That is a fast use of eutectic alloy commercially. Earlier people were aware about the low melting point, fluidity of eutectic alloy, but commercially eutectic alloy, lead-tin alloy was used by Johannes Gutenberg in manufacturing type. And we know that this invention or application changed our civilization and Renaissance in Europe. That is basically the driving force for Renaissance in Europe. And the first official foundry was established in Moscow. They call it cannon shop for manufacturing cannon. And die casting was patented in England sometime mid of 19th century. Commercialization of solidification and casting technology were accelerated by Alfred Krupp. He was a very powerful businessman dealing with almost everything, starting from arms to railway wheels. He has a wide coverage. So he invented centrifugal casting for manufacturing axisymmetric components like tubes, discs, rings for weapon and railway application. But all these were based on experience and imprecise knowledge of the skilled worker. There was no science as such. There was no solidification science clearly established. There was no phase diagram. Gibbs published his paper in 1875, between some time in series, in parts, between 75 to 78. And surprisingly, it was a very obscure journal in America. I mean, Connecticut Academy of Arts and Science, nobody knew that. actually it is Arrhenius who popularized this paper. And this is the foundation of equilibrium of heterogeneous system, where we started learning the free energy, kinetics, microstructure, grain size in scientific manner. And it is mid of 19th century where significant transformation happened in mechanical science. Steam engine, machine tools, combustion engine, rails, all evolved during mid of 19th century. And in tandem, the melting, solidification and casting technology also evolved in complementary manner. For casting, for manufacturing pig iron, they required some machines which were provided by inventions in mechanical science. At the same time, castings were used for the expansion of mechanical science, for more accuracy, for more precision of steam engine, combustion engine, like that. And the breakthrough happened with the invention of arc furnace, electric arc furnace by William Siemens in 1878, followed by invention of induction furnace in 1890, which we are still using, which are major source of manufacturing casting. Okay. So the early, second half of 19th century and early 20th century, that was mostly popular for design and application of machines, right? And it was based on Gibbs theory of solidification. But people gradually, and it was basically, concept was equilibrium. People gradually understood Gibbs' concept of equilibrium of heterogeneous system doesn't work in practical application of solidification. It is basically non-equilibrium. And a parameter which we are aware of, undercooling, was identified to describe the non-equilibrium features in solidification process. And it is a parameter which is not precise about the material or process. It evolves during the process through the contribution of several parameters like kinetics, constitutional undercooling, which is basically function of entropy and free energy, thermal undercooling, which is basically function of enthalpy, pressure undercooling, which is basically curvature of the solid liquid interface, kinetic undercooling, which is transport of solid from liquid to metal, and R is basically pressure it is radius undercooling. This is basically curvature. C is constitutional cooling, it is thermal undercooling, pressure undercooling, kinetic undercooling. So different parameters contributing to the undercooling, and by virtue of that, some driving force was achievable. Because at equilibrium, nothing transforms. When delta G between two phases is 0, it doesn't transform. Something has to happen so that the energy reduces. And this difference is the driving force for solidification. So this was basically a parameter which was correlated with the non-equilibrium feature of the process. Similarly, people used Gibbs theory for development of phase diagram in wide range of alloy. But this phase diagram was basically equilibrium diagram. For example, when solidification proceeds at an average composition, the common metallurgical concept is that we determine fraction of solid as this length, this opposite arm, it is composition of solid, this is composition of liquid, so this arm divided by this arm. So that we call lever rule. This is equilibrium concept. But it doesn't work in solidification process. So the equilibrium, and during this period, people were trying to go for computational development of phase diagram. But this equilibrium concept was not working. So Schill proposed an equation of non-equilibrium partitioning, where Cs is the concentration of solute in the solid, K is partitioning coefficient, C0 is the average composition, and fractions transform. So it is partition in terms of fraction transform. That is, during the course of the process, you could interpret the partitioning behavior of solute across the liquid-solid interface. So this was basically used in CALFAD. Even today we are using CALFAD as a very useful software for assessment of phase transformation, and Shields' equation provided the incorporation of non-equilibrium feature in CALFAD process. And for industry, one breakthrough happened in assessment of shrinkage and eliminating shrinkage, which was proposed by Voronov, is absolutely empirical. Simply, this is the time of solidification is basically ratio of volume and surface area of a particular component for a given shape. It is like this: when most of the metals solidify, there is a volume shrinkage, and we need some external feeder to compensate the shrinkage in volume. Now, suppose this is a location of external feeder, and if there is a choke which is having lower volume to surface area, so that hinders the liquid to flow to the shrinkage, right? So the design should be like this, where there should not be any choke and riser can flow in a direction where there is continuous increment in V by A ratio, and that is basically even today foundation of methoding of casting. We do not go for computation, we do not go for finite element analysis, finite volume analysis, but we basically rely on Voronov's rule, a single 2-parameter equation. And similarly, one of the difficulty was that solidification occurs in different morphology, ranging from dendrite to columnar to equiaxed, right? And it is very difficult to predict because this happens during solidification which you can't see. What is happening within the mold, you can't see. You just pour the liquid metal and you take out the casting. What is happening in between, that is a black box. So people didn't know what kind of microstructure can evolve. So for that, they identified 2 parameters, that is temperature gradient and growth rate, which you can measure. And as a function of this, they could map the different kind of morphology, starting from planar to cellular to columnar dendritic to equiaxed dendritic. So that shows under which condition, which kind of morphology selection is possible. And second thing, it is expressed in terms of G by R ratio and G into R, that is in this direction, which shows the tendency of refinement of grain. If you follow this direction, dendrites gradually become finer and finer. So that's how an empirical foundation for solidification process was established. I will request to remind me 5 minutes earlier than my closer so that I can go in the next slide. I don't want to miss the last slide. Yeah. So once that is there, the next step was microstructure engineering. People knew what is the driving force, how to manage undercooling, how to manage morphology. But how to manage the microstructure? Say for aluminum silicon alloy, which is an eutectic, basically there are 3 kind of invariant reaction, popular invariant reaction in solidification: eutectic, peritectic, and monotectic, right? So eutectic is most common. This is a common alloy, aluminum silicon alloy. So if you go through silicon content, the microstructure will vary like this. The primary phase, you will get coarser and coarser primary phase, that is silicon, and which is very brittle. So people wanted to get rid of this coarse, brittle silicon in aluminum matrix, and for that they adopted some grain refiner like titanium mustard alloy, titanium boride, or some modifier like tin, antimony, cerium, which modify the shape of the eutectic, right? So that's how they could engineer the microstructure. Similarly, this is a silver copper eutectic, right? And it is possible to allow this eutectic to form in a directional manner. If you impose a heat transfer in this direction, so the 2 phases, aluminum, silver and copper, which are mutually insoluble, which remains as a silver and copper phase during eutectic solidification, you can develop directional growth of these 2 phases. Now it may happen, so if you remove one of the phase by etching, you can develop nanowires. So this is one of the method for development of nanowire by engineering the eutectic solidification, or else you can develop nanopores. Similarly, in aero engine or combustion system, you need single crystal because there is a typical loading direction where polycrystals do not provide the necessary strength. Usually, when you allow the material to cool, it gives you polycrystal. And you can get rid of this polycrystalline feature by two methods. Either one, you remove the source of nucleation. You remove all the inclusions, all the precipitates, and you impose a unidirectional heat transfer. So that gives rise columnar grains, and you have the low angle boundaries mostly. So these are single crystal, which is very popular in superalloys for application in aero engines. I'll go fast. So while we were doing all this, still we were not aware about what is happening between melting point and solidification point. Most of the alloy has a range of solidification. There is a temperature range between solidus and liquidus line, and we do not know what is happening there physically. But most of the important features are happening there because this is a massy state. This is semi-solid state, right? And conventional CFD, it is very difficult to apply conventional CFD in these cases. Professor Jha is there, perhaps he understands. This is non-continuum system. So people try to understand, and this is the region where during solidification there is a shrinkage in the solid. Once there is a shrinkage in the solid, there is a drop of pressure in the liquid. Once there is a drop of pressure in the liquid, there is reduction in solubility of gas, and it gets supersaturated, it evolves gas heterogeneously, and that gas creates bubbles, nuclear bubbles, and they remain within the liquid, and that is the source of porosity. And it is not a single pressure. There are multiple pressure acting on that: atmospheric pressure, metallostatic pressure, shrinkage pressure, and surface tension. So they constituted an empirical equation to predict the possibility of formation of gases in the massy state. Similarly, NIAMT proposed a criteria in this form where T is the local thermal gradient, G is the local thermal gradient, and T is the cooling rate. So if you plot NIAMT criteria, you can find different values where there is no shrinkage, there is micro shrinkage, and there is macro shrinkage. So empirically, you can predict the occurrence of kind of shrinkage during the solidification in a massy state. Similarly, people determine different criteria for hot tearing, mechanism-wise and concerning conditions and causes. So what I mean, this is a stage. It happened during, second half of the 20th century when people deterministically started predicting the happening during the casting process. It becomes a bit predictable. Earlier it was only trial and error, so gradually it became predictable. And once people understood the happenings in the massy stage, they were interested about getting rid of that. So Spencer and his group in MIT, they were conducting some experiments on lead tin alloy to reduce the solidification stress. And they found that when they are applying, it is sometime around 1700. So, 1970. So when they apply stress, when they apply shear stress, the solidification stress reduces. And it was found that application of shear stress reduces the viscosity, shear rate reduces the viscosity following this non-Newtonian equation, where K is the a consistency parameter, and n is the flow coefficient, gamma dot is the strain rate. So they could find a way out to reduce the viscosity in the semi-solid stage by application of shear. Not only that, application of shear fragments the dendrite, and these fragmented dendrites provide the nucleation site for fresh grains. So they could transform the dendritic microstructure to equiax microstructure, and that opened up a new direction of processing metal, liquid metal, which is, they call it rheocasting, where liquid metal is forced with some shear force within the mold cavity. It is another version of die cavity, but with some shear. And the other is rheocasting, where a billet is heated at between liquid and solidus line, that is semi-solid stage, and forced in a die. So there are different varieties. Professor Amitesh Kumar is working in a slope casting, where shear is applied during the movement of liquid through the slope. So there is different process, but idea is application of shear. Now here, some more parameter came into the scenario apart from the shrinkage of the liquid, behavior of gas, convective percolation of liquid within the dendrite. It became the behavior of viscosity and stress of the liquid. So the constitutional framework of semi-solid casting is really complex, and it needs strong mathematical framework to predict some outcome. And many people are now working in this area, so they are coming across such difficulties, but at the final, we can get rid of dendritic and columnar microstructure, and we can produce equiax microstructure. And by that, we can eliminate another step of heat treatment. Another
Sir, 5 minutes.
breakthrough in solidification.
Sir, 5 minutes more.
5 minutes or?
More. Yeah.
Okay, so I'll move fast. People found that liquid can be supercooled even below melting temperature if you increase the cooling rate, right? So in 1940, Kauzmann proposed that there must be a temperature above which you can cool the Kauzmann temperature, above which you can cool the liquid and you can have amorphous phase. And Paul Duez in Caltech produced the amorphous phase, but it was a strip, small thickness, very high cooling rate. Later on, people started designing multi-component alloy and started processing the melt so that they can eliminate the source of nucleation like impurities, etc. And by that, and they identified that there are some alloys. I'll go a bit faster. If you give 5 more minutes, I can justify that. So there is a line which is solid liquid equilibrium line. So if you cool the melt within this region below a temperature, you can form glass. And this was the invention of Kane in Caltech in 1970 again, and who can produce metallic glass with 10 millimeter diameter, some useful component. And this is the way you can reduce the cooling rate. You need to shift the CCT curve, because in this region you will have supercooling, and if you cross the CCT line, you will have crystallization. So the idea is to shift the CCT curve by designing multi-component alloy and processing of melt. So now one can produce glass with a cooling rate of 10 to the power 2 K per second in comparison to 10 to the power 6 K per second what Paul Duez did. And these are the alloys, family of alloys where you have solidification, metallic glass. I mean, change in slide taking time, that bonus I should have. Yeah. So basically now people understand the solidification is not an unique phenomena at unique scale. It is convoluted outcome of phenomena happening from nano to meso to micro to meso to macro scale. It is a convoluted effect. So it is basically multi-scale phenomena, and people evolved different mathematical framework to compute the phenomena happening at different length scale. So this is macro and mesoscale, where the phenomena are mold filling, thermal field, force field, At micro scale, these are nucleation and growth. At nanoscale, this is liquid to solid ordering and evolution of properties. In atomic scale, for all these computation, you need some constant. And these physical constants for many metals, particularly for new alloy systems, are not available in kind of handbook. So you need to compute that. And that computation is possible only if you have access in atomic scale. So that is how different computational systems evolved, and this evolved independently, but subsequently they were linked together. They are linked together in the sense, say, at macro scale, they compute temperature, cooling rate, etc., and that can be the input for microscale computation. Similarly, for microscale computation, they can determine solidification, fraction, and microstructure. That can be an input for macroscale computation. So that is how all the scales were integrated together, and that's how they could compensate limitation of one scale by the outcome of others. And capability of one particular scale can be the input for the others. So that's why they have developed a computational framework, and this has been used in a large number of simulation software nowadays available for solidification. So they are the range of simulation softwares which cover a wide processing methods of casting and which can predict different kind of defects, a wide range of defect using different kind of CFD simulation software, either finite element, finite difference, finite volume, whatever it is. So with that, so far we have discussed top-down process. We have discussed solidification process, some bulk liquid filled in a bulk cavity, and we have allowed to solidify. Carl Drecker was a student of metallurgy in Texas University in 1980 when I took the admission. So basically he understood that there are three directions of metal shaping. One is solidification, other is plastic deformation, and third is powder metallurgy, sintering. And powder metallurgy is a bottom-up process. So it occurred in his mind, can we, and that time laser was very, very popular. In 1970, laser was used for cutting titanium. In 1974, AFCO Everett, a company, they evolved a machine as such for modification of surface using laser. So laser was very attractive, so he thought that, can I use laser for sintering powders? And he proposed that to his supervisor, Joe Beman. They started working together, and in 1987, they got the patent of laser-assisted sintering. And that opened up a new era of processing metal component, where powder is either dispensed through a nozzle or it is laid on a plane and is energized by laser beam, right? So it is line of sight process. There is a focus, directed energy beam, which scans along a track, repeats the track, and complete a two-dimensional layer, and they build up one layer after another to build up the three-dimensional component. But the phenomenology here is basically governed by, this is energy concentration under the laser beam. It is laser power. V is scan speed of the beam. H is the distance between hatch, and T is the thickness, right? So you can have a plot between scan speed and laser power which depicts the outcome. In some cases it is complete melting, it is some cases fully dense, over melting. So essentially you can predict the kind of defects. Whether it is balling or shrinkage, that kind of defect you can predict from these parameters. Phenomenologically, under the laser beam, there are thermal radiation, thermal conduction, absorption and reflection of energy, and there is also a turbulence. And there are different complex mechanisms which takes place here, because this is basically capillary effect. There is no large scale solidification behavior of metal pool. So it is melt pool dynamics, evaporation, Marangoni effect. In other cases, surface tension is function of temperature, but here surface tension, it depends on temperature gradient, weighting. So there are several complex phenomena. Most importantly, in most of the cases, they found dislocation soft cells, which we find in cold work material. In cold work material, density of dislocation is basically to the level of 10 to the power 9 meter per meter cube. But here it was 10 to the power 14 meter per meter cube. It is comparable to severe plastic deformation. So this is a process where solidification, plastic deformation, and powder metallurgy merge together. So it is a convoluted phenomena of three independent approaches of metal shaping. So far the computer, I'll take 2 minutes more. Am I allowed? So far, the computational framework and process framework were independent from each other. People developed a solid model in CAD that is transferred to processing system. The processing system follows whatever are there in the model and they develop the component. Similarly, in Procast, we model the casting, solidification in a separate place, and we do the casting in a different place. That is not supposed to work here because this is line of sight. This demands that material, process, observation, feedback, and control and correction of defects, they should go simultaneously across the time and space of process, which requires a designer should have the access to define and evolve the shape, process, and product within his design framework. It needs integration of sensors and control system, and for that it needs in situ measurement of temperature, cooling rate, stress evolved. It needs measurement of dimensions because layer after layer the dimension changes. There are distortion. One layer will affect other. And the surface quality, which are the difficulties people are coming across. It is essential. Well, I mean, the barrier is the build chamber. It is confined process. You cannot invade the build chamber. So there should be options for dynamic CAD system, which can exercise the design during the process itself based on the measurements and back propagation loop. And yes, you can have very good camera, you can have very good sensors, you can collect data, you can collect signals, you can collect image. But the processing should be very fast. So that when you are scanning one hatch, that data is processed to predict the probable defects there and to control the parameter of the next hatch to compensate this defect. Or it has to assess the defects supposed to occur in one layer, and during laying the next layer, you have to control the parameters which will take care of compensating the defect in the previous layer. So that should be the kind of automation we are expecting in future, maybe next 10-20 years. Then I believe this 3D printing will be effective for commercialization, where we will have the product which will be comparable for machine to machine, for one build to other build, and from one place to other. That is where market will rely you, otherwise it has got no commercial value. Thank you very much.
Thank you, sir.
And finally,
so we have a nice session.
This should be the goal of any manufacturing process.
That's right.
Are you happy to answer any question? Otherwise, I'm available around. Huh? Yeah.
Professor Chattopadhyay, it's a very brilliant presentation and a very brilliant study. And you have done it in such an easy and lucid way that it becomes very easy for non-engineering people to understand the whole thing. And you have actually taken out the 6,000 years of history of metal casting in a cup. I have certain queries and certain observations, which I would be very curious to know from you. The metal casting industry in Indian subcontinent, you know, like if we go back to the early Harappan Saraswati civilization, and if we look into the metal artifacts which were found in Sortogai in Afghanistan, or for that matter in the pre-Harappan sites in Helmand River of Afghanistan, and also Rakhigari in Haryana, and Mehergarh and Lothal in Gujarat. We see that the artifacts which came out, you know, like, I mean, these are at least more than 6,000 to 7,000 years old, if not earlier. I was looking into a study of the Archaeological Survey of India day before yesterday. Some of the new artifacts which they have discovered in Rakhigari as well as in Mehergarh, and the carbon dating which they have done of that, it shows that it's at least around 8,000 years old. And if we look into the metal casting of the Indian steel, you know, the Watt steel or the Damascus steel, and also the artifacts which were discovered ahead of Bhet Dwarka and in the submerged part of Dwarka, you know, there is a continuity, and it seems to be a fantastic process through which the Indian metal casting industry developed. So have you done a study of that in relation to
How much time do I have to answer your question?
5 minutes, I think, or 2 minutes?
I have just covered the solidification part, but there is other elegant part of artisanship of India, that is forging and welding. Right? You have mentioned Damascus sword. Actually, wood steel were manufactured in India in 500 BC. Right? And recently, Professor Balasubramanian of Madras IIT, he is no more. So he has investigated in details the structure of iron pillar and Damascus sword. And it is now established that in Damascus sword is basically fine martensitic matrix where there is dispersion of carbon nanotube. It was, I'm talking about 500 BC, maybe earlier than that. How this happened? How could carbon nanotube, and not only carbon nanotube, iron carbide impregnated within that, how it could happen? Actually, during that period, they were using wood lugs for stirring the metal. And this is the organic constituents of wood lugs which transformed into carbon nanotube during solidification. Right? Not only that, perhaps I was sharing yesterday, Hyder Ali and Tipu Sultan could develop rocket, the fast time in the world, and whatever we do, that is easily hijacked elsewhere and patented somewhere else. Well, so there are a lot of things to understand, and it is not just we find and get it. It needs research. I mean, we are talking about ancient knowledge system, and there is a lot of opportunities in metallurgy, because if you see, history is something, epic is something, archaeology is something. If you fail to converge these three in a framework of historiography, that is reliable. And for that, it needs extensive research and obviously extensive funding. That is my appeal to Government of India to provide fund to young engineers who are engaged in that.
May I add something? You
Yes,
know, one of very senior foundry person from Pune, he has presented a paper in World International Foundry Congresses. And he has given the scriptures. He was a B metallurgy from COP Pune. At the same time, he was a MA in Sanskrit. So that was his passion. So he learned the Sanskrit. And then he has, in the ancient scriptures, he has read the process of investment casting documented in Sanskrit. And it tallies with our latest and modern manufacturing process, how to collect the honey, or from where you have the wax, how you make the slurry, how you make the pattern. And you see all the idols in the old days, they were casted with the investment casting with the process which is already scripted in the Sanskrit in long time ago, maybe before BC, I don't know how many years before BC.
So all these
And
castings are lost wax process.
Yeah, and then one more phenomenon I want to see. Rather, I want to suggest that for all engineers, if they really want to know the birth of a knowledge, the roots of the knowledge, they should learn the Sanskrit, because there are Sanskrit scholars, they don't understand metallurgy, and there are metallurgists, they don't understand the Sanskrit. But you have metallurgists having good expertise in the Sanskrit, because Sanskrit is the typical language where in couple of lines you have the 3-4 pages of a knowledge encapsulated into that. So if you, rather my appeal, I mean, a few of the students over here, if they could start learning Sanskrit, maybe after 10-15 years, they will be masters in Sanskrit, so they can really understand what is written in those couple of shlokas, in that couplet, and that will carry a good meaning. And that's how that is the way we can take the roots of the knowledge, and we can enhance our knowledge base. That is what my suggestion is.
Sir, your suggestion, please allow me to put in my words. It is like someone manufacturing cycle, he need to learn how to ride a cycle. Manufacturing cycle is a mechanistic precise affair, and riding cycle is an imprecise. But it's a knowledge. Unless and until you know how to ride a cycle, it is not possible to manufacture a cycle. Thank you, sir.
So very good discussion. So this session we have 4 papers completed. First from the Professor P.K. Jha from IIT Roorkee. He presented on the composite seat making. The second paper from Professor Rajiv Asthana from the USA. He presented on the weightability on that. Third paper from China. That was on the lubrication part. And the fourth from our own director. And now the fifth is from the Tata Steel. He's not here? He came, I think. So it is now, as discussed, that is simulation is important. So this is another, that is Magma Soft is here. And they have a sponsor also here. So we give 2 opportunity them to present his view and show his things in that, what MagmaSoft can do for the solidification and this.
Ladies and gentlemen, I have an announcement to make. The 2 research papers by authors Mr. T. Niranjan, on behalf of whom Mr. Kuntal Maji was presenting, and Ms. Anushri Datta of this session is now shifted to lecture hall, 2nd floor, admin building due to shortage of time. We are very sorry for the inconvenience caused, and I request the authors to please cooperate. Anyone interested can join the session there. We gratefully acknowledge Magma as the sponsor for this presentation. MagmaSoft is a leading casting design and simulation software that empowers foundries to optimize their processes. We are delighted to have Magma representatives with us today. The title of their presentation for ICAFFT 2024 is Stresses in Sand Casting Analysis and Optimized Solutions for Improved Casting, Designs and Product Quality. This work was conducted by Jesper Thoborg, Georg Zimmerman, and Corina Thompson from Aiken University. The presentation will be delivered by Kedar Jugdar and Rohit Bhardwaj. I request the speakers to please come up to the dais. And I would request Professor Dr. Kamlesh Kumar Singh to please welcome the guest speaker with flower and a token of appreciation as a symbol of respect and gratitude.
Thank you, sir. Thank you, sir. I'll
Very good afternoon to everyone. Namaste, Vandanam, Namaskaram, Vanakkam. It's been a long time I have been on stage and it's a bit stressed today. Let's not be frank about it. So I'm from Magmasoft. My name is Kedar Jugdar, and with me my colleague is here, Mr. Rohit Bharadwaj. We have been working with Microsoft from past 1 year and more. And we are here to present a case study on stress simulation in sand castings. So to speak a brief about it, I would like to thank the management from NIAFFT, and today it's been recalled as NIAFT, for calling us, and it's been an honor to be here and to present the paper. And also I'm overwhelmed with the last day's performance and the presentations I've seen, because this is the first time I have been here in NIFT and in the conference. I'm glad, and I'm also envied that I have missed the opportunity to work with NIFT in the past times. So Magma, unlocking your potential. From the past decades, not even a long time, the foreign countries have been speaking about Foundry 4.0. From past COVID times in India, we have been speaking about this sustainability thing. Not even sustainability, we also speak about lean manufacturing, or else we can say optimized resource utilization and power savings projects. To improve all the projects and to sustain in the market, we need to first get the quality out consistently in the casting development. Only when we have the quality consistent casting, then we will be able to improve the processes. Here comes the Magma into a play, where we offer a Pinnacle software which enables you to utilize the tool to predict the upcoming defects inside the castings. Not only the defects related to porosities or restricting to filling and solidification, but also related to stresses and deformations. Like we can speak about heat treatments. What can be wrong, what can go wrong with the heat treatments? We can fail to obtain the microstructure or the mechanical properties. We can also define that. Apart from that, we can also check the stresses inside the casting. So due to residual stresses, we have seen some cases of field failures. We can also predict. To bit brief about Magma, it was founded in the year 1989 by Dr. Elwin Frender in Germany, Aachen, where they worked with a small team of experts, from metal experts and some developers. And today we have grown up to 240 plus employees, working in and around the globe, making Magma's global presence. Apart from this, we also have networks with R&D and R&D networks in and around the globe who are working with us to develop the software, aiding supports and operations. We also have 9+ independent subsidiaries in and around the globe, including India. We have been supporting in their operations. We have been supporting in their operations and developing castings, and helping them to establish the quality consistent casting premise. These are our customers in and around the globe. We have more than 3,600 plus customers with multiple licenses opted by each. In India, we have more than 136 plus installations with multiple licenses opted by many individuals. And in India, we have a code delivered by the customers. Wherever they find the casting, they find Magma. This is Magma's running history from past 35 years. As I said, it started in the year 1989 in a GIFA as a prototype. And with industrial demand, it has been evolved with developing first module in LPDC, then later on to HPDC, iron, steel, then convection, segregation, heat treatment, then stresses. And not only that, we have also developed some of the modules in CC castings. And then in the last year, 2023, we came up with the 3rd generation software, which is giving a pinnacle again in prediction of defects in the foundry industry. And in the year 2024, just past month, we have announced the latest update of 6.1, but it is yet to be released in this market industry. And not just offering the software to use, we also provide training and support operations to the customers who have purchased the softwares from Magmasoft India. Apart from this, we also have training sessions in Hyderabad office, which is our headquarters in India, where we provide trainings with individual dedicated systems, where you can use the tools and help yourself to get familiar with it efficiently. Okay. Further will be carried by my colleague.
So, hello again, Johar, to all my NIFT faculties. They have been very helpful for my academic. I did my master's from this college, so it is a pleasure to be here. So this is a paper from Jasper Thorberg, Corina Thompson, and Zimmermann from Aachen, Germany. We are presenting it on their behalf. So, so in this paper, we are going to talk about stresses in sand castings and what are the challenges we are going to face. So there are a few case studies we will talk about. So first of all, what are the challenges we face in castings? Basically, as if we talk about the stresses which are developed during solidification processes. So first of all, this is a versatile process, everybody use it. And design complexity is like we can also cast complex designs in sand castings. Stress defects, if we talk about them, then they are majorly cold cracks and hot tears. So what residual stresses looks like? This is a demonstration video that how catastrophic a residual stress break can be, which need to be eliminated before any supply to the customers, because any field failure will be a catastrophic event. So, as this is a lattice, which demonstration lattice, we will talk about that, and we will check the simulation results, how we can eliminate them using those tools. So, what are the benefits? Obviously, quality assurance and also dimensional accuracy. If we talk about stresses, because there are contractions. So, what we get from stress simulations? First thing is that in thermal interaction metal contracts. Sometimes we have expanding sands, like green sands expands much. And outer regions get cool first, so that's why the tensile stresses build up in castings. And later the stress evolution during cooling, what happens that at high intermediate temperatures, the hot tears appears. And after solidus temperature, there is a chances of cold cracks. So as you can see the image that stress relaxation over time for large castings have a different impact on the stresses. Like we call it like creep viscoplasty effect. If we see that in large castings, what happens that because casting is having a lot of time to get cooled, the stress relaxations as per creep effect, they will relax the stresses within the castings. So simulations benefits, what they do that predict the stress evaluation defects and what are the dimensional changes are going to take place. And so that's how we can enhance our design. So we will talk about few case studies for large castings. So what is the challenge? That is long cooling time. In these cases, what happens that we are not able to predict what are the relaxations that are going to happen in our stresses within castings. So that's for we have a unified creep model, which will predict time and temperature depending behavior. So here is a case study of main energy solution casting, where the focus is on residual stresses state prediction in cast cylinder, cast iron cylinder. So we are going to validate a ring core method for that by doing milling and creating notches and releasing the stresses and also simulating them with the software also. So what are the key findings? Stress measurements will align better with the unified grip. Okay. So this is an example that we saw that how the stress lattice was breaking on just making a notch out of it. So what is the process when we are simulating as a whole piece? Then there is a stress build up in the thick section of the casting. And later if we are doing a ring core method, then their simulation demonstrated that there is zero stresses remaining in that region. So there is another case of gray iron frame. So next what we learn about after that, we have to locate the locations in casting where we are going to do that. So in this casting, what was the challenge? That large stress gradient was detected during simulations. So the sensitivity of the measurement tools, like we do surface grinding and we do like use strain gauges. So that accuracy of that where we are going to put them or where we are going to measure them, that was needed to be evaluated before. So as we compare the simulation results, so the similar trend, but quite some difference like from the absolute values of the results. But finding was that the critical areas which are prone to the high stresses. So the measurement using simulation, we planned it before that where we are going to put them. So after learning from the previous example, so we took another case of ductile iron frame. So what we did, we clearly point out the places where we are going to use those gauges and all. So what we found, that unified creep model was demonstrated superior agreement. The curves that are matching is demonstrating the creep module results. So what were our observations? The unified creep model successfully show us what is the relaxation, how it is going to happen in the large castings. A ring code method is very effective. But very sensitive to prepare and measurement location. So we have to identify the locations before doing that. So what is other things in stress modules and other? There are we have to fulfill dimensional requirements in castings always. So the one thing is flatness and roundness. So there is another case study. There is a cast iron electric engine cover. So what was happening, that there were a lot of vibrations in that. So during prototype testing, what we suspected that there is some dimensional instability and residual stresses might be playing a role. So what was the goal? That we have to evaluate flatness and roundness of that casting. So what simulations, these are the setups. And these are the measurements where the locations of the roundness we are going to measure. So there we use a 6-point measurement technique. These are the volume stresses results, which are causing deformation around the inner sections and the outer layers of the casting. And this is a section view where high volume stresses around the ribs was causing bending issue. So this is the comparison between simulation and physical measurements. So we draw a graph, and the agreement was there, flatness, roundness results were totally matching with this. And there was actually what was measured was 0.276 and what was simulated was 0.9. Which was close, particularly, so we are able to predict. So this evaluation, what it did that we had heat treatment was not needed for that casting, and there was a lot of saving of money. And vibration issue was unrelated to that process, resolved by R&D without like any process modification. So there is another thing for stress, like we have to minimize hot air risks in some castings. Like we use DOE, like we use variable designs and do simulations on that. So what are the causes of hot air? Obviously, uneven cooling causing thermal contractions, poor feeding causing porosity and outsource. And what are the results of that those hot airs and that repair buildings we have to do and high scrap rates? So what is the solution? That is thermal analysis and the identification of the hotspots and the locations, and stress line analysis to like strain wherever strain is developing, those zones we have to identify. So we have to pinpoint those areas, and like this is case study where we were able to predict by simulations that which regions the hot airs might form. So also in actual we were getting the same results. What was the outcome? That optimum feeder design we did improved to increase the feeding efficiency, and the reason was that there are narrow feeding paths that were causing hot airs. So another case study is like yoke casting, where like you can see there is a corner where we are getting hot air. So we identify those four key zone all in a casting. So we did that we did a virtual design of experiments where we perform multiple designs in simulation and see which design would be the best for us. Objective was to minimize hot air criteria and minimize porosity creation also. So for that we did okay. So these are the 12 designs. Like we try to change those risers locations and that feeding efficiencies of the risers. So what are the results we got? So these were the like comparisons between all the results, where in left we kept reduced porosity, and in right we kept reduced hot air. So what was saying that there is opposing trend, that if we are going to increase feeding, that is going to reduce porosity, but that will increase the hot air, and vice versa. So what is the optimized outcome? That in the middle you can see that we have a compromised state where we have the less porosity and we have the less hot air effect. So this is the best possible compromise. And so when we simulated that, and we actually what we found out, that the hot air risk was reduced by 60% comparison of the previous design, and the feeder layout was changed around 30%, and casting geometry was changed like we had to change around 44%. So this was the final result we got, and like obviously there was no risk for hot air anymore. So risk of cracks during machining. So what happens is that maybe casting might be okay, but after machining we found that there are cracks developed in casting. So there is another case study where there is a large cast iron frame. It has several holes. So once we casted it, it was okay. But when we started to do drillings and all operations, like crack appeared and casting got rejected. So this is the as cast part which we simulated. So here we find that only 57 MPa of stresses are developed there. But after machining, we found it that the region was having around 234 ampere around stresses in there. So like it was having a crack issue in these parts. So what we did, we prepared 3 designs for different methoding and like a few process changes. So in first case, what we did that we put a chill between those holes to to fasten the cooling rate of that region. Second, we filled those holes and we make it like later we will machine the holes also. And in third case, we increased the load carrying area, like we added some extra metal to it. So what would be the best results? We will see. So this was the original design where we were getting 234 MPa of stresses at that region. But after putting a chill to a casting, it was reduced to 152. And we saw that when we filled it and later machined it, then it didn't help much. And also when we put ribs, there was no improvement also. So the best case was the putting a chill between those holes only. So another like what we can analyze in stress is also when we quench the castings. So what do we get? So this is a ring brake disc. So what we are going to do that we are going to use 2 different quenchants. One is water and one is oil. And 2 different quench conditions. One is homogeneous and the second one is inhomogeneous. So objective is to minimize the distortion during quenching process. So these are the 6 permutations, combinations, things that we get as homogeneous water quenching, inhomogeneous water quenching, and we get the results of those, and with oil also. So what we found that in the 5th image that we have the least distortion in the X direction. In the distortion factorized by 15 to visualize better. So first case that is like maximum difference is only 1 in X direction. So this is the best case for us. Where top side was quenched faster, and rest 5 cases were eliminated. And also there is one more thing, that is integrated distortion control in casting during heat treatment. So this is a component, this is a very big blade, turbine blade, which has a size of 4.5 to 3.5. Like our aim was to minimize the deformation in solidifying cooling and also minimize the deformation during heat treatment. So what we see here that initial deviation was 22 mm, like maximum deviation. The images are blurred a little bit, but you can see by the color. But pre-shaping by adjustment, like if you get the results from simulation, we can do the pre-shaping of CAD adjustments, and we reduced the deviation to 6 mm. So what was the outcome of this? The accurate patterns of 6 blades, like we did 3D scanning, and we found these results. Like the green color is showing the simulation results, and the blue is showing the actual measurements. So this is how the blades were positioned for the heat treatment and after machining, preparing for NDT. So we what we found that during heat treatment, the relaxation at high temperature, like that was very good in core areas and or thick areas of the casting. And quenching, that high stresses were increased, but they were acceptable at the end of the cycle. It was only 20 MPa around, so that was acceptable in thick sections also. So also the direction of deformation we got from the simulation, that it will be upward in center and downward in the thick sections. And the deviation of 6 to 9 mm was observed, which was within tolerance. Okay, thank you, sir.
Thank you. So both you have presented nicely. So have any question? I think sir first asked to something.
Okay.
Well, no, I mean, it's a good presentation. What I feel, simulation software we use, with the basic principle of a thermal equilibriums and cooling rate.
Okay.
And what we want to, what we look forward is to have the even cooling rate all along the geometry of a casting, basically, right? So when we do the simulation for any component, then we observe when we select the methoding through the simulation software, what should be the feeder, what should be the in-gates and all. We take care of all these things. And then we look forward to have a proper casting out of that.
Yes.
And to support that, whatever you are describing about the problems, what you face, the prediction of the problems, whatever the internal stresses or shrinkages or whatever you have said about in a couple of case studies. I think then that is the reason why we use, while during the simulation, we put the shields, we put the sleeves, exothermic sleeves and all, and we take maximum care of all those problems.
Yes.
Then what is extra in this model, what you are introducing to us right now, than the previous model of a simulation software? Because as it is, these things are happening.
Yeah.
Only you are defining the problems. You are defining the problems or anything extra in this model. I will like to know that.
Okay, like from the magma perspective, you want
From
to know
the magma perspective.
Okay. Yeah. So, like recently, sir, this creep module is developed. That what we so that the viscoplastic module. So it is like recently like very developed and research module, and recent updates we are like getting more better results than previously. So what is happening? The relaxation state, the other previously we were not able to predict them. Yes, yes, yes.
That's fine. Thank you.
Okay.
Sir, excuse me. Sir, I would like to add some few more points on this. To answer you precisely on the question you have raised, I will go back few slides. As we spoke about uniform cooling, that will help our casting to get a good consistent level in all the bunches we produce. This is what we have proved here. In this, if you look at the slides, we have used two type of quenchants. I will brief a bit about it, what the case study was. The casting was developed and had no deformation until it was knocked off. Only when the casting was taken for heat treatment, it had some bends and deformations in the X and Y axis. To compensate that, the team came up to Microsoft in Germany and they asked for some solutions, how it can be predicted and what can be done to avoid them. So they had a facility of water quenchant and oil quenchant in their premises. So our team gone with a solution that we will do some homogeneous in water and inhomogeneous in water, plus the same cycle will be followed in oil. In this inhomogeneous, they also try to do some changes in the process, like flipping the casting and checking, while in heat treatment we know we use agitation fans. If you use it in the parallel to the casting, it will be homogeneous on all the sides. If you use it from the bottom, it will be acting immensely on the bottom side. As we know in quenching, there are three main processes that defines the distincts the quenching process. First is vapor jacketing that forms when the casting is immersed into the water tank, and then second is the boiling phase, and third comes the convection phase. So what they tried first in the water and the oil, they gone with the homogeneous one and they checked what is the deviation between these two phases. In oil, they had a deviation of approx 1.7 mm in homogeneous. In water, they had a deviation of 2 mm. They were not satisfied. They said we have to be bit reduced because the limit was 1.5, the tolerance given to them. To compensate, they again came with the different 4 different actions in homogeneous quenching. They used agitation fans to cool the casting from indistinct directions, from the bottom, from the top again, just by flipping the casting. The fan will be rotating from the bottom and it will be cooling. It will be hitting the vaporized surface so that the increased area will be dissipating the heat from the casting as early as possible. In this way, they came approx, in this 4-way, they find out that in homogeneous oil quenching, the top side of this casting, when this top side is quenched faster, only then the casting is having the least deviation because of the ribs formation. So the theory what we have been speaking about, the consistent, equalized, uniform heat dissipation will help the casting, not in this case. it was inhomogeneous. This can be predicted with the help of software, and it has been matched with the shop floor. So this is the pinnacle what I have been referring to.
Sir, we are running too late.
Yes, sir. No time. Yes, sir.
I just have two queries for you. I have seen the list of companies with whom you are working here in India.
Yep.
Yeah, but I do not see any government components in it, with any government companies or with any government departments. Does your company, Magma, have any proposal for working with something like, say, Coal India, or for that matter, with the Indian oil companies, the PSUs? And do you all have anything concrete in relation to Mission 2047 under the Make in India program to be given to the government of India? If you all have that, then probably in that I can, give you all a support and we can actually work out something.
Okay.
But if you haven't worked with the government department so far, why is it so?
Sir, to clarify about it, I would say government departments don't just produce the casting by themselves. They also consume casting from outside.
Absolutely.
So the OEMs has the software.
Have you all tried to, sell your, your technology and your, or bid for your technology with the government departments? Because many multinational companies are doing that. I know several Israeli companies, as well as companies from United States of America, as well as from UK. And from France, they are trying it. The model which you have developed is quite, it's quite modernized and it's very specialized.
Yes.
So have you all tried on that front or not yet?
From my experience, I know that there are a few talks between the companies, but again, I don't know how fledged it went and what was the hindrance point between them and why it stopped. Even with NIFT, I think it has, you should have got the
We
software
can
from the
discuss
past year
later
itself.
on in the lunch time that you can discuss.
Yeah.
We are going too late. It is coming 1 and we have the next session and that will come, lunch will be delayed then. So we have 2 main presentation in that session. One from Dr. Rahul Kumar from Tata Steel and one from Professor D. Ravi from IIT Delhi. And to other presentation is also there that maybe you have to see how you can manage it. Okay. So now you can start the next session. Quick. And tea can be served in the inside itself. Tell them to serve inside itself. Yeah.
Good afternoon, everyone. We are now about to start the second technical session of Day 2 of the International Conference on Advances in Foundry and Forming Technology 2024. Now, I would like to invite our chairperson for the session, Professor Dr. N.K. Singh, who would lead the session with his expertise.
He is not here. He is in meeting. You can just continue.
All right, sir. Dr. D. Ravi Kumar is a professor in the Department of Mechanical Engineering, IIT Delhi, and presently the head of Central Workshop. He received the Institute Teaching Excellence Award and the Outstanding Young Teacher in Mechanical Engineering Award. Dr. Ravi has carried out a number of research projects by DST, ISRO, and DRDO as principal investigator and consultancy projects sponsored by Tata Steel, Cessna India, John Deere, and Tube Investments of India Limited. He has also served as the member of Board of Governors NIAMT Ranchi since 2017. I would request Sir to please share his valuable insights. I would like to request our session chairperson. Yes, sir. Okay, sir. I would like to request our former Chairman Board of Governors, Sri Sham Arjun Wadkar sir, to please welcome the guest speaker with a flower and a token of appreciation as a symbol of respect and gratitude.
Can I have next slide here when you make it full screen? I can change the slide from next one. I just want to see the next one. Hello, sir. How are you? Thank you very much. Thank you very much. Thanks a lot.
this is the opportunity for me.
Thank you very much. Thanks a lot. Yeah, this is what I want. Yeah, yeah. Yeah, yeah. Sure. I don't need this. No? Good afternoon, everyone. Sir, how much time do I have? Because I was, initially I thought I had 45 minutes because it's 1.5 hour session. So I made my slides accordingly. Later I was told it's about 30 minutes. So now, what is the time? How much? Yeah. Okay, so 30 minutes. 25. Thank you very much. So I'll skip some slides and I'll try to cover everything. Good afternoon, everyone. Yeah, thank you very much for the introduction. So I'm Ravi Kumar from the Department of Mechanical Engineering at IIT Delhi. And my today's talk is on importance of sheet metal formability for lightweighting automotive sheet metal parts. And we heard a lot about casting in the last presentations. So I would like to take all of you into a different domain from micro to macro, where we manufacture, large parts and so on. So before I go to my talk, I'll just take 1 minute to give an overview of what we are doing at IIT Delhi. We have been involved in metal forming research at IIT Delhi for the last 26 years. And my primary area of work is sheet metal forming. And within sheet metal forming, we work on various aspects, both experimental as well as simulation work, including the finite element analysis of various conventional and unconventional sheet metal forming processes, formability analysis, prediction of defects and spring back, and unconventional processes like hydroforming, warm forming, forming with Taylor welded blanks, and deep drawing textured dies, and so on. We are also working on plastic deformation to enhance the properties of sheet metals. Apart from sheet metal forming, some of my students in our group are also working on bulk forming processes such as rolling, extrusion, forging, and so on. Yeah. So these are some of the facilities that we have in our sheet metal forming laboratory at IIT Delhi. We have a customized formability testing machine, and we have a few hydraulic presses equipped with computerized data acquisition systems with tooling for various sheet metal forming processes. We have a laser grid marking machine for strain measurement, and we have a few software for simulating the various metal forming processes like Q-form, Dynaform, Autoform, so all kinds of forms. And then we have a cold rolling mill which is also used for cryo rolling of aluminum alloys, and a few other such facilities. Yeah. So coming to today's talk, as we all know, a large number of complex sheet metal parts are required for manufacturing, various parts for automotive. So as you can see here, some of the parts are so complex that they can't be manufactured using any one single process or using any one single step. So to convert a flat sheet into the final component, it has to go through a series of operations before we get the final part. Okay, and we all know the various common sheet metal forming processes are deep drawing, in every process, Yeah, these are some of the common sheet metal forming processes which are used in the industry to manufacture various parts. And we all know about these processes. So in each process, the state of stress, is different at different locations, and it also varies from process to process. So one common thing in all these processes is that the sheet metal undergoes a significant amount of plastic deformation before we get the final shape. So therefore, the ability of a sheet metal to undergo the required amount of plastic deformation without any defect or thinning, excessive thinning, is extremely important for us. And there are a large number of applications for these processes. And all these processes are carried out on various kinds of presses, mechanical presses, hydraulic presses, and pneumatic presses. And so therefore, apart from the materials forming characteristics, we are also interested in the tooling design, the machine parameters, and various other process variables. So now, coming to the lightweighting of automotive sheet metal parts. So now in automotive industry, there is something that everybody talks about is, a lightweight vehicle. So we want to bring down the weight such that the CO2 emissions can be reduced and the fuel economy can be improved, and there are so on. Okay. So how do we do that? I mean, just as an example, a 10% reduction in car weight can lead to 6 to 8% decrease in fuel consumption. And similarly, the sheet metal parts like body panels and various other tubular parts in a four-wheeler, it constitutes about 30 to 40% of the total weight of a car. And it's about 30 to 35% in a two-wheeler. So if we can bring down the weight of the sheet metal parts, so the overall weight of the vehicle can also be brought down. So what are the different approaches for lightweighting automotive sheet metal parts? So some of those techniques I would like to discuss with some case studies, including our own work. So one is, in conventional forming, it is possible to reduce the weight of a sheet metal part by reducing the initial blank thickness, either by using the existing grade, if it is not possible, or if we have a better advantage, we can go for an alternate grade and reduce thickness further so that we can bring down the weight. And second one is by using some tailored blanks, either tailor welded blanks or tailor heat treated blanks to achieve certain specific advantages apart from reducing the weight. And third alternative is to replace the conventional steel with lightweight materials, and the most prominent of them is the aluminum alloy. So by using aluminum alloys, wherever it is possible, if we can replace steel, we can bring down the weight. And lastly, by using some alternate manufacturing process such as warm forming and hydroforming, it is possible to use materials with thinner gauges, and also it is possible to use materials with lower formability so that we can enhance their formability and use them in place of the conventional materials. So I would like to just touch upon all these four things, very briefly, because I don't have much time. But before talking about these four techniques with some examples, I also want to give a very little background about formability. Why, to explore these approaches, which is the best one for a given application, why formability of sheet metals is extremely important. Yeah. So you can see, as I have already defined, formability is the ability of a sheet metal to undergo required amount of shape change and the required plastic deformation without any defects or thinning. Okay? A defect need not be a fracture all the time. It need not be a crack. It can be something else also. Okay? And it is a very complex thing because there are a large number of variables which influence formability simultaneously. And how do we evaluate formability? Formability is measured in terms of, for example, in certain contexts we talk about the maximum strain a sheet material can undergo, or the depth to which a sheet can be formed in a given forming operation, or the maximum thinning it can withstand before the failure takes place. So these are some of the measures of formability. And this formability is influenced by a various number of variables which can be categorized into design variables, process variables, and material properties. Material properties we all know, we're all talking about in the last few lectures also. Strength and ductility are always important. But apart from that, the strain hardening ability of a material is also extremely important, particularly in cold working operations. Strain rate sensitivity index is also extremely important, particularly in hot working conditions. And apart from the material properties, we are also concerned with design variables and the process variables. When you design tooling for a given forming operation, so the design variables are fixed at that stage. What you can control during the process is the process variables, like blank holding force, punch speed, the temperature, okay, and so on. But unfortunately, we don't have any one single index to say that the formability, overall formability of the sheet is this much. We have a large number of tests to evaluate formability. So for example, a limiting dome height test is shown here. We use a hemispherical punch to deform a sheet until a visible necking or failure is observed. So here the edges of the sheets are completely clamped so that the material undergoes pure biaxial stretching. So it gives us a measure of stretchability. Similarly, if I want to determine drawability, we have another test called Swift flat bottom cup test, where we measure the limiting draw ratio, the maximum possible draw ratio, which can be achieved without any failure. Similarly, there are many other tests, Ericsson cup test, Fukui conical cup test, and so on. In every test, the mode of deformation is the same. So every test will give you formability of a material in one particular mode of deformation. But suppose if I want the limit strains of a sheet metal in all the possible modes of deformation, then we evaluate a diagram called forming limit diagram or a forming limit curve. So as you can see, this is a plot between major principal strain and minor principal strain measured on the surface of a sheet after deformation. So you can clearly see that this diagram tells us to what extent a sheet metal can be formed in any mode of deformation before the localized necking or the failure takes place. Often, even though we call it as a curve, it is plotted as a band consisting of an upper limit and a lower limit. So if the strains fall above the curve, it means that the material is definitely going to fail. And if the strains measured on the surface are below the lower limit, it is definitely going to be a safe operation. But if the strains are within these two limits, within these two curves, it means that the material is likely to fail. So that's the critical region. So that is how the forming limit curve is plotted, but it doesn't come from any one single test. We need to carry out a large number of tests. The most popular method is Nakajima method, using which we can evaluate the limit strains in different modes of deformation by changing the geometry of the sample. Okay. So where is it useful? How can we use this forming limit curve? There are two uses of this forming limit curve. One is to predict failure. The second one is to diagnose failure in case there is a failure in a certain component. So you can see here that there is a component and certain regions in this component are extremely critical. So what do we do in the development stage? We do laser grid marking or stochastic pattern on the component. We form the component. In critical regions we measure the strains, and those strains are superimposed on the forming limit curve, as you can see. So if the strains at any location are going close to the FLC or above that, it means that the operation is not going to be successful. We need to rework on either the process variables or the design variables. But if the strains on the component are well below the forming limit curve, then it means that it's a safe operation and those parameters can be implemented in the shop floor. So, and this is a very simple thing. For a very simple object, it is easy to measure strains and superimpose it on the FLC. But often in the industry, we have components with very complex shape, and we quickly need the strains on the formed component. So what do? We use the finite element analysis or simulations to quickly predict the strain distributions, stress distributions, and so on. So in the finite element simulations, to predict whether failure takes place or not, the experimentally determined forming limit curve can be used. Even though it has its own limitations, but still it serves as a general failure criterion for quick visualization of the success of the forming operation. Okay, and if we don't have the experimentally determined forming limit curves, they can also be predicted using some analytical relations. So that is also possible. So here you can see the finite element simulations of some simple deep drawing operations, the deep drawing of a square cup using hydroforming, spring back prediction, and so on. I'm sorry, it's not running. No, I just wanted to play this. So here all of you are familiar with these finite element simulations, but I just want to. No, it's working here. Okay, I think we'll leave it because I don't have much time. So. Which one? No, this one. So I'm sorry, the video is not playing here. So this is stamping of a car door panel in the finite element simulation. And you can see on the left hand side corner of the forming limit curve of the material. And the strains predicted from this simulation are directly superimposed on the forming limit curve. And if they're exceeding the limit, then it indicates failure. So we need to rework on the variables so that we can take the remedial action. So in this way, the formability analysis, either by experiments and also by simulations, are extremely important to predict failure and also to diagnose failures. Sorry. No. I have come back to the normal file. That's not opening. Let me just see. Yeah. So now I talk about the lightweighting of some sheet metal parts using those 4 approaches that I have already mentioned. Okay. So you can see here we are taking the example of a 2-wheeler fuel tank on the motorbikes that most of you must be knowing. So presently it consists of 3 parts. Okay. And out of that, the upper left and upper right parts have a very large depth. They are manufactured by deep drawing. And there is a third part at the bottom, which is like a fixture at the bottom, that is also formed. And these 2 upper and lower parts are deep drawn in the same die. Okay, they are like mirror images of each other, and then they are welded by big welding process. And once this is joined, and this one is joined to the lower part by seam welding, and this is the final complete fuel tank that you can see. And this is presently being manufactured by most of the two-wheelers using one grade called extra deep drawing steel of 0.8 mm thickness, irrespective of the model and irrespective of the forming severity. So we just tried a few different options to bring down the weight of this fuel tank, and yet it should meet the required functional regulations. Okay, so one is by reducing the initial sheet thickness with the same grade. What is the minimum thickness that at which it can be produced? And if we change the grade to a better grade with better formability, then what will be the minimum sheet thickness with which it can be produced? And the third option is, instead of making these two parts separately, whether we can make the entire fuel tank in one single step using an alternate manufacturing process, that is hydroforming. So these are the alternatives that we just explored. So you can see here the comparison of material properties, the general mechanical properties and formability parameters of these two, extra deep drawing steel. The second one is IF steel, which is interstitial free steel. And even though the strength of IF steel is slightly lower than the EDD steel, but the strain hardening exponent and the anisotropic parameters are higher, indicating its better stretchability and drawability, so that the overall formability of IF steel is definitely better than that of EDD steel. And this is the finite element model which we have created for simulation of the fuel tank, and I don't want to go into each and every detail. And this is the material model that is required to define the hardening behavior and the yield behavior of the material in any software that we generally use. So we have used Autoform software, and this is the hardening curve as per the Swift hardening model, and this is the yield surface of the material, plotted using Barlath yield criterion, using Barlath 89 criterion, and this is the forming limit curve of the material which is experimentally determined. And here you can see some simulation results of the fuel tank, of the two-wheeler fuel tank. Initially we started with EDD 0.8 mm, so just to validate the existing data, and iteratively we reduced the sheet thickness without changing the grade, and we went down to 0.7 mm. Still the operation was successful, and the strains on the component predicted were much lower than the forming limit curve, and it clearly shows that we can go down to 0.7 mm without any this thing. So one of the major requirements is that in the final formed part, the minimum thickness at any point, at any location, cannot go less than 0.5 mm. So that was one of the requirements apart from the other things. And when we changed the grade to IF steel, we have seen that by doing a large number of simulations, the sheet thickness can be further reduced to 0.65 mm. So that would reduce the weight even more. But it would slightly cost more because IF steel is costlier than EDD steel. So we need to see where is the balance. Okay, and so you can see the maximum thinning in different materials, about 27%, 28%, and 23%. And this shows the major strain and minor strain distributions in the simulated parts, and we can see that IF steel can take larger amount of strain, and in this portion we have seen both the strains are highly positive, indicating that there is a large amount of biaxial stretching in this portion where the depth is maximum. But in the other regions, the material is drawn from the wall, from the flange into the wall region. So to resist thinning in the wall, drawability is also extremely important. So therefore both stretchability and drawability are very important to manufacture this part, even though we generally say fuel tank is made by deep drawing. But stretchability is also extremely important. So now, just to explore what is the minimum possible thickness, we went down to less than 0.7 to 0.68 in the case of EDD and 0.63 in the case of IF steel. But at that time, we have seen that the parts can be successfully formed without any problem. But the only thing is, thinning was more than what can be tolerated. So you can see that the minimum required thickness is 0.5, but the simulations have predicted that if the initial sheet thickness is 0.68, the minimum thickness would be 0.486. And in the case of IF, if the initial sheet thickness is 0.63, the minimum thickness would be 0.47. So that doesn't fulfill the requirements of the present standards. So therefore, we finally concluded that 0.7 and 0.65 are the minimum possible sheet thicknesses at which the fuel tank can be manufactured. So then with these new thicknesses and the new grades, we have carried out the actual fuel tank manufacturing in the industry. Okay, so you can see a 600-ton double action hydraulic press has been used. All this work has been done in the NCR region, and we have used a advanced strain measurement technique called GOM to measure the strains on the deformed fuel tank parts. So we can see the the comparison between experimental and simulation results for different grades and different thicknesses. And experimentally also we have seen that EDD with 0.7 and IF with 0.65 can be safely formed without any this thing. And these are the simulated and experimental results for maximum major strain, maximum minor strain, and maximum thinning. So within with a small discrepancy, the predicted results agreed well with the experimental results. And the next alternative is to use aluminum alloys in place of steel. So we have chosen two aluminum alloys, both belonging to 5000 series, because 5000 series belongs to work hardening alloys. They have very high work hardening ability. 5052 has been chosen because that is being presently used in two-wheeler industry for a few other sheet metal parts. And in the annealed condition, it has very low strength. So therefore, we used in the solution treated, partially cold worked and naturally aged. That is H32. That's the most common temper in which this sheet is used. And the second one is 5754. Since it has enough strength and formability in the annealed condition, we used it in the annealed condition. So you can clearly see that 5754 has much better strain hardening ability, even though the drawability of both the materials is much inferior when compared to steels. So we started the simulations with 1 mm, and this is the determination of forming limit curves for both the materials experimentally, and these forming limit curves have been used as the failure criterion in the simulations. And this shows the predicted results and the experimental results on aluminum alloys fuel tank manufacturing, the actual fuel tank. So we started with 1 mm. In both the cases, we were not able to form completely to the required depth. You can see 5052 failed when the part depth was 122 mm, and 5754 failed at 162 mm, whereas the required depth was like 180 mm. So, and experimentally also you can see that there was a complete crack, and there was excessive thinning, and the material failed in both cases. This was anyway expected because the sheet thickness is equal to steel sheet thickness. And experimentally measured strains also, you can see they have far exceeded the forming limit curve, and this was what was expected. So then we predicted formability of these two alloys for fuel tank manufacturing by enhancing the sheet thickness. So we went up to 2 mm, and 5754 we found that if the sheet thickness can be increased to 2 mm, it can be successfully formed, and the minimum thickness would be 1.4 mm. I know the aluminum alloys are costlier, okay, and if you increase the sheet thickness, it would be even costlier. But the thing is that the weight of the component will still be lower even if it is 2 mm. But in case of 5052, even at 2 mm also, the predictions were unsuccessful. I mean, unsuccessful forming. The actual press trials could not be done with aluminum alloys with 2 mm, because the current tooling in the industry was made for 1 mm sheet. The tolerances and the punch and die design clearances and everything were made for 1 mm. So therefore the press trials were not done. So just to give a comparison now, so EDD steel 0.8, if we can reduce it to 0.7, it gives us about 12.5% weight saving for this one particular component alone. And similarly, if we change the grade to IF, which has much better formability than EDD, we can even go down to 0.65, so that would give a weight saving of nearly 19%. And if we completely change the material to aluminum, but we need to increase the sheet thickness to 2 mm to prevent any failure. But in such a case, we would get a weight saving of 15%. So if you look at the cost, it is highly negative in case of aluminum. But what we expect is that if this kind of simulation methodology is followed for various other components, and if we can reduce the weight significantly down, in the long run, the improvement in the fuel economy would actually offset the cost saving. I mean, it would offset this negative cost saving. Okay. So now we talked about how much time do I have? I have another 10 minutes. 5 minutes. Okay. So we just talked about different grades of steel. By changing the grade, how we can reduce the weight and all that. There is another thing called tailor welded blanks or tailored blanks, where in one single component itself we can combine several grades of steel or several grades of steel or same grade of different thicknesses, so that the weight can be minimized and the cost can also be reduced. So these are called the tailor welded blanks. In 90s, it was a new concept, but now if you see, the tailor welded blanks are being used in various automobiles, in various four-wheelers and so on. So the main advantages of these tailor welded blanks are mass saving, cost saving, and better technical performance. You can see here some even books are written exclusively on tailor welded blanks for advanced manufacturing. So this is the process details. Let's suppose say conventionally this component contains 4 different parts, and they have to be formed separately and they are spot welded. But now using tailor welded blanks, what we can do is that we can choose the correct thickness or the correct grade for 5 different blanks, which are cut according to the required shape and size. Prior to forming, they're all laser welded, okay? Because laser welding is a very fast welding operation, and it also gives you a very, very, narrow heat affected zone. So after laser welding, this composite blank is formed into the final component in one single forming operation. So 5 forming operations have become one single forming operation, and all the subsequent spot welding operations have been eliminated. And so the process becomes much faster and easier. More than that, the main advantage is that the design engineer now has a lot of flexibility to choose what kind of thickness he should use at what location, what grade of steel he should use at that particular location, so that he can tailor the blank according to the final functional requirements. So wherever you require higher stiffness, we can have it higher thickness. And wherever you require higher strength, you can use a high strength steel grade, and in other portions you can have a low strength grade. So because of this flexibility, the tailor welded blanks have found a lot of applications in automobiles. So here you can see a blank with a laser welded this thing, and then it is formed. You can see the weld line here. So this gives you a lot of flexibility, and here also we can see the weld line. And there are a lot of case studies, how much weight we can reduce and how much cost we can reduce. Of course, the cost saving comes into picture only when you produce a large number of parts and in a long run. And you can see B-pillar, front rails, rails, there are so many other parts, fuel tank. Weight saving, you can see 32%, 34%, 25%. So by using tailor welded blanks, it is clearly possible to reduce the weight and cost in the long run. But when it comes to forming of tailor welded blanks, there are certain challenges. If you have one single sheet which has the same properties everywhere, it is very easy to predict everything because the material behaves in the same way. But now I have a tailor welded blank, I have a weld line in between. On one side, for example, I have a thicker sheet. On the other side, I have a thinner sheet. Similarly, I have one grade of steel on this side, one grade of steel on the other side. So the material behavior changes because the properties are different. And the weld region itself behaves in a different way, because usually the weld region has lower ductility when compared to the parent sheets. And in addition to that, you have a small heat affected zone. So it is important to consider all these things when we design the tooling, the process variables, when you form the Taylor welded blanks. So therefore, the most important factors that need to be considered when we are forming the Taylor welded blanks are the difference in strength and or thickness. Look at the weld and HZ properties, the thickness ratio, okay, and the weld location and orientation, because the weld orientation is also extremely important. Here you can see examples of two parts where in one case we have a longitudinal weld and the other one we have a transverse weld. So the orientation of the weld with respect to the direction of loading also plays an important role. You can see on the right hand side the Taylor welded blanks which are like a normal sheet continuously. Here you can see the finite element simulation of a limiting dome height test for a Taylor welded blank. Here you can see on one side you have one kind of strain distribution, on the other side you have another completely a different kind of strain distribution. And when you define the material model, you need to define 3 material models for parent material 1, parent material 2, and for the welded region. So it is important to determine the properties of the welded region also, so that our simulations are more accurate. So I will just skip this because I don't have much time. So lastly, I talked about alternate forming processes for enhancement of formability so that we can further bring down the vehicles. One is, since aluminum alloys are lightweight, we are always attracted towards them. But one major drawback is their formability at room temperature is generally inferior when compared to many low carbon steel grades at room temperature. So therefore, one of the techniques to enhance formability of aluminum alloys is warm forming. We all know about cold working and hot working. This warm forming is somewhere between the two. We are working at elevated temperatures but below the recrystallization temperature. So it means that we are trying to combine the advantages of both cold working and hot working to a certain extent. But at the same time, of course, we have the disadvantages of both at the same time. So you can see on the right hand side the improvement in formability of aluminum alloys at elevated temperatures. As you can see, as the temperature increases, the forming limit curve moves up. Okay, so it means that you have better limit strengths. But the parameters that affect formability in the warm working temperature region are much more complicated, because we have certain parameters related to high temperature. One is temperature itself, the other one is the properties which get influenced by temperature, mainly the strain rate sensitivity index. Because for most of the common metals, the strain rate sensitivity index at room temperature is close to 0. So the change in punch speed is not a major parameter. But when you are working at elevated temperature, the strain rate sensitivity becomes extremely important. So therefore, the punch speed and all that, they also become a fact. Okay, and so you can see the improvement in formability of a automotive component by warm forming. On the right hand side, you can see there is no crack in this location, whereas this is the part which is formed at room temperature, and this is the part which is formed at elevated temperature. So lastly, hydroforming is another alternate process which can be used to enhance formability of lightweight materials or materials with lower formability in conventional forming. So again, hydroforming is of two types. One is tube hydroforming, the other one is sheet hydroforming. In tube hydroforming, a tube is internally pressurized such that the tube bulges out and it conforms to the die configuration. Okay, sometimes in addition to internal fluid pressure, we also apply axial load such that the material deformation becomes more precise and you can form accurate components. So I am mostly interested in sheet hydroforming. So you can see here, in sheet hydroforming, we use fluid pressure to bulge a sheet or to draw a sheet into a die cavity. That is pure hydroforming. The other alternative is you form the component by a conventional mechanical force, and at the same time the sheet metal is subjected to counter pressure by the fluid pressure. So that gives you some special advantages. So lastly, I just want to show one more small case study. I'm going back to the same fuel tank again. So now we have considered a fuel tank with much larger depth. So now you can see the young people know in bikes you get more, intricately designed fuel tanks, so there are some of the fuel tanks have very large depth. So this particular model has 220 mm depth. So we have done simulations to see whether this fuel tank with large depth can be manufactured as one single component by hydroforming, which is not possible by conventional forming. And before that, we have found out they are presently using EDD 0.8 mm steel, so we have used the same material so that there is no need for any change of material. And we have found out initially from simulations as well as experiments, lab scale experiments, what is the maximum pressure up to which this sheet can be formed by hydroforming. And we have found out that it can go up to nearly 20 to 21 MPa, that is 200 to 210 bar. Okay. So after experimental validation of this, then we carried out the hydroforming simulations. So we have found out that in one single stage of hydroforming, it is not possible to achieve the entire depth. So here we can see the failure in single stage hydroforming. You can clearly see the failure at the location where the depth is maximum. That is where the material gets stretched biaxially. And here we can clearly see that the strain path is towards equibiaxial tension. Because this is fluid pressure, there is no friction. So the material gets stretched equally in both the directions. And so since we were unable to form the entire depth in one single stage hydroforming, we have gone for two-stage hydroforming. In the first stage, we were able to form up to 184 mm, and then this simulation data has been imported as the initial starting data for the second stage. And in the second stage simulation, we could successfully form the fuel tank up to the required depth of 220 mm. Okay, but the only problem that we have seen is that the minimum thickness after second stage forming has gone down below 0.5 mm, which is the present requirement for a fuel tank. So what we have thought is that by introducing an intermediate annealing treatment between the first stage and second stage, it is possible further to improve the strain distribution and reduce maximum thinning. So with that optimization, it will be possible to produce this large depth fuel tank in one single stage hydroforming with minimum required thickness above the required value. So this is just another case study for hydroforming. So with this I finish. I'm sorry I have exceeded time. I have cut down from 45 minutes to 25 minutes. So as I just mentioned, the formability analysis is extremely important for lightweighting of automotive sheet metal parts. And there are several approaches, and we just explored a few options, and this is what is talk about. I'm sorry I had to skip some slides. Maybe some other time I'll talk about them. Yeah, thank you very much.
Thank you very much. So you can take one question if you have, just otherwise in lunchtime you have a discussion that can be done.
Yeah,
okay.
I'm here till 4 o'clock.
Oh yeah, okay. Thank you, sir. Thank you, sir. So we have a next presentation from Dr. Rahul Kumar is here, I think, yeah, from Tata Steel R&D.
Dr. Rahul Kumar is a prominent researcher at Tata Steel, specializing in material science and engineering. His research has contributed to the development of advanced high-strength steel with improved formability and impact resistance, which are used in various applications including automotive, construction, and infrastructure. I would like to invite Sir to share his valuable insights. And also I would like to request Dr. Suvra Kamal Datta to please welcome the guest speaker with a flower and a token of appreciation. Okay. I would like to request Dr. Parthapratim Chattopadhyay to please welcome the guest speaker with a flower and a token of appreciation as a symbol of respect and gratitude.
I hope I'm audible at the back. So before I start, I would just like to, thank all the organizers, mainly Professor K.K. Singh, Dr. Manoj Kumar, Dr. Himanshu, and of course Chakravarti sir, whom we have been knowing for quite a long time. In today's talk, what I am going to do is, I'm going to cover some of the research what we have been doing in Tata Steel. And as you know, Tata Steel is in the business of manufacturing flat steels largely. Long product also we make, but not that much. And mostly whatever we make, actually that's for the construction, where the forming is not that important a subject. The flat steel what we produce, a large part of that actually we sell to the auto manufacturing companies. And just for the information, we sell about 3 million tons of flat product to the auto manufacturing companies in India, which is about 44% of the steels which is actually used by that industry. So it's a very large industry. And therefore the sheet metal forming is very, very important. Okay. What I'm going to do is, we actually do research which actually focuses on all aspects of the sheet metal forming. It's the computation, the experiment, and also the new forming technologies. So what I'll do is, I'll try to cover all of them, a glimpse of all of them. So accordingly, I have divided the slides into different segments. Before we start, in industry, we are actually asked few questions very often. And those questions is, what is the impact on the business? That's the very most commonly asked questions in industry. The second is, if you are going to work on a particular project, what is going to be the ROI on the investment? These terminologies, as a researcher, we didn't know when we joined the organization, but over a period of time, we become expert in, using that as per our convenience. We are also asked a question which is very, very common, is what is the mega trend, where the industry is moving. So what I have started doing lately is start the presentation with a mega trend. So if you look at some of the trends, then you will realize that globally there are certain things which is going to happen for sure. And one thing which is going to happen for sure is the energy is going to be greener, and possibly the energy will also be cheaper, which many people will not believe, but if the technology breakthrough happens, then it may become quite cheap also. The second is AI, which is already there. Okay, generative AI and all sort of stuffs are there. People have started writing papers and the thesis also using ChatGPT. Sensorization is also very, very important. It is already there. And next stage, the quantum computation. So maybe in another 5 to 7 years time, the quantum computation will be there. Now, how all of these going to affect? Okay, and my focus in today's talk is going to be how some of these are going to affect the automotive industry in general and the sheet metal forming industry in particular. Okay. Now, if you talk about energy, it is certainly going to affect the automotive industry. The automotive industry is going to migrate, which is already happening. It is going to be electric vehicle, right? Now, if you look at some of the things, here I have tried to show a comparative picture of two vehicles of almost same size. If you look at the dimensions, it's almost same. But the weight, if you look at, it's significantly different. And the weight difference is because of the battery weight. The battery weight is typically 300 to 500 kg depending on the battery size. Now what happens, one immediate impact of this is, once the crash happens at the same speed, now you have to absorb more energy. And the formula is very simple, half MVA square. So if the M increases, your energy absorption capacity of the vehicle has to be increased, and therefore you have only two options. Either you increase the thickness, which will actually impact adversely the range of the vehicle, or you use high tensile steels. okay, so that you absorb more energy without actually increasing the weight. Therefore, steel industry has been for some time now working extensively in developing newer steels, newer advanced high strength steels which can be used by the industry. However, there are certain problems, okay, and which is very much visible from this banana curve, because once you increase the strength, the formability, like in the previous talk, Dr. Ravi Kumar talked about the formability actually gets adversely affected. So making the component becomes more and more difficult and tricky. Okay, and one classical problem is basically the spring back. So if you see, the amount of spring back increases significantly if you move from mild steel to 980 megapascal steels, which is actually dual phase steel, right? So there are certain challenges. But at the same time, if you look at the industry trend from 2016 to 2020, the usage of these advanced high strength steels has increased significantly. And this change has been much rapid if you compare the rate of change with European market. And the reason is much of the information and the knowledge both for production and usage of these steels are now known. Because initially when these steels were getting produced, developed and produced and used, there were a lot of challenges. Those have been more or less addressed. So the information is readily available, so the adoption is much faster. Now the thing is, why a steel company should actually work in that area? So like I said that we actually produce steel and sell a significant amount of steel to the automotive industry. So we also feel that it's our duty to also give the know-how while using these steel to the users, that how to use these steel, how to solve the problems associated with these steels. And one of the most common way of solving those problems is basically the simulation. Okay, the finite element simulation, a large part of that in the previous talk, it was already covered. Okay. However, there is a challenge. And the challenge is the simulation accuracy of the commercial software is still not that good for certain types of steel under certain conditions. So I'll just show you that what are those conditions. But before that, I'll try to bring in a concept of a strain path, because this I am going to use quite a few times during my talk. So what is the strain path? So suppose you are making this dome shape and you take focus only on one point, and you keep on measuring the major and the minor strain. In another word, in X and Y direction, you keep on measuring the strain at a different time interval. And you keep on plotting here. So suppose when there was a flat sheet, no deformation, both the strains were 0, 0, and then you plot. If it's a straight line like this, you call it a linear strain path or proportional deformation. But if it's not a linear, suppose it changes, okay, and it's not a linear, or there is an abrupt change, so it's a non-linear deformation. Now if you are trying to make components like this, each point, each material point will have its unique deformation path. And to be able to predict this deformation accurately, you should be able to predict the whole deformation for that path very, very accurately. And I'll tell you what is the challenge in that. Now what happens when you are deforming a sheet which is very thin? So basically that other two dimensions are quite large compared to the thickness, so we can safely assume it to be a kind of a plane stress deformation, right? So if we consider it as a plane stress deformation and simplify the thing, so there are certain things you need to know for the simulation. One is when the material will start deforming plastically, right? Because the metal start deforming plastically after certain stress. And the second is, if you continue deforming it beyond that yield point, what happens? Now, if you ask this question, it's very easy to answer in uniaxial case, right? You just do a tensile test and you say this is a yield stress and this is the hardening curve, etc., etc., etc. But here, as you could understand, that it's actually a biaxial deformation. So the right question now is that what combination of the two stresses will cause the material to deform plastically, right? And the second is what happens if we continue deforming it further, right? So these two questions have to be answered by any model. Only then you would be able to simulate it more accurately. Now, if we try to design an experiment, then that experiment probably would be something like this. You take a small piece of sheet, you apply a stress this direction, apply a stress this direction simultaneously, and note down the point, the combination of sigma 1 and sigma 2 where the material start deforming plastically. And if you repeat it many times for different samples from the same material, and you just plot that locus of those points, actually it will be something like this. This is nothing but the yield surface, which we have been studying in our undergraduate, first year, second year. Like the von Mises yield criteria, Tresca yield criteria, that is nothing but just the equation of this surface, right? Only thing is that they actually gave the equation, and later on this proved through some experiment that yes, each point actually lies on those surface. But this is what? So actually we can give our own equation, right? The easiest way is just to give a nth order polynomial which will fit into any sort of curve. However, this only tells you the initial yielding. What happens if you further deform it? So the evolution of this surface, right? So this gives you the initial one, but there are two issues: shape of the surface and the further evolution. The shape is basically related to the texture of the material, because what shape exactly it will be, that will depend on what is the texture. And further evolution is the hardening. Now the hardening is actually very, very complicated, because depending on what strain path you give, okay, the shape of this, the further evolution is going to be impacted, right? However, it is very, very complicated to model that in any mathematical framework. So the people have tried to simplify it. And one of the easiest simplification is you say isotropic hardening. What is isotropic hardening? You just say that irrespective of what deformation path I assume, it is going to increase by equal amount in all the direction. This means if I give a simple tensile deformation in this direction, so it has increased from here to here because of the strain hardening, but it has also increased in the reverse direction. So if I do, after deforming a small amount in the tensile, if I do compression, actually it will tell me the same yield stress, right? However, the reality is not like that. The Bausinger effect is a well-known phenomena, right? It's actually the lower. So it's not the correct representation, but this is very simple. 95% of the simulations in the industry actually uses this, and therefore one of the reasons the accuracy is not there. A little bit more complicated, you say, it doesn't only increase in size, but it also translate. And that rate of translation and the direction of translation actually will depend on the material and the deformation path. Okay, and then you have to devise some experimental procedure to characterize that, because then you have to calculate what is going to be the rate of translation and the direction of translation through some experiment, because the model itself will not work unless you give some input, material input. So this is, but by the way, it's called combined hardening model. Now, what I'm going to do is I'm going to show you some applications of this. So in Tata Steel, we have developed in-house material models, advanced material models based on combined hardening models, which gives us better accuracy compared to the available commercial softwares like PAMSTAMP, LS-DYNA, or Abacus for that matter. Of course, some of them also started using advanced material models now, but this gives better accuracy. So just let me show you some examples. So what we did is we designed this experiment. And this experiment actually, it's a very simple experiment, but it's a very good experiment for simulating non-proportional deformation. So actually here, we made a hat section. Now if you make the hat section, in this region, it is going to be bending and bending. Okay, so bending and bending, so basically straightening. Okay, so the deformation will be plane strain tension, unloading, and then plane strain compression. So that is how it is going to be. What we did is, we added a little bit of complexity to that. And what complexities we did is, we took samples like this was the base material, Then we did some experiment only with the base material without which was fully annealed samples. Then we also took this material and we gave some pre-strain. So we actually did some tensile deformation, about 5%. And then we made samples from the center, and then we did the 2D draw. Okay. So if you see, what does it mean? It means we do deformation in this direction in the second case, unloading, and then you make hat. So the top section or the top layer of the material will actually experience deformation like this: tension, then unloading, and then plane strain, tension. So this is a non-linear, in a controlled manner, a non-linear deformation path. Now the simulations were done. So this is the experimental results. 3 samples were tested just to check the repeatability. The repeatability was very good. And then this is the pre-strain. Here also 3 samples were tested and the repeatability was very good. Then the comparison between the two were done only for the shape, the experimental comparison, and you can see here the pre-strain is having higher spring back, and the reason is because of the pre-straining, because of strain hardening, the strength has increased, and since the strength has increased, the spring back will be higher. And then the simulation was done. Now, and the simulation was done using the in-house developed material model, and this is for the base metal, and you can see for the base metal the prediction is very good. Okay. But when we started doing the simulations for the pre-strain, it was actually not working. So basically when we say with softening, without softening, actually we are talking about the 2 different material models. So you can see with softening actually predicts very well, whereas the without softening doesn't predict it that well. Okay. So we said, okay, you need to have advanced material models with softening, etc., to be able to predict the spring back more accurately. The second area where we are working a lot is because one of the problem with such type of methodology is that you do not have or many people do not have the experimental capabilities or facilities to carry out advanced tests, because some of these material models also require plane strain test or equibiaxial test, which is not available readily. So how do you do that? How do you still use this? So we came up with the concept that can we do a virtual experiment? Now, how do we do the virtual experiment? So this is something like this. So suppose we want to use this yield criteria, even the Hills 48 yield criteria, we need to carry out 3 experiments, which is easy in this case because you just do the tensile test in 3 directions, 0, 45 and 90. But if you want to use Hills say 90 yield criteria or Ballard's yield criteria, you need to do equibiaxial test, etc., that facility is not there. So we came up with a concept where actually you can simulate this thing virtually. Now, how do you do that? So the one way of doing that is you start doing crystal plasticity based finite element analysis. Now, what is this? So we actually start now doing the deformation modeling, finite element deformation modeling of individual grains. Okay, and the process is very simple. So basically what do you do is, so suppose you have a chunk of grains, so suppose you have 1000 grains, orientation you can actually calculate using EBSD, etc., and you can actually superimpose that. Otherwise, if you want random, you can do random also, and then you assume some critical result shear stress values initially, and what do you do is you apply a stress and you see that whether you are able to simulate a very simple deformation like tensile test or not. And once you do that, basically that you do to calibrate some of the coefficients, like the critical result shear stress is not known a priori. So you start with some assumption and then you calibrate that to come to a value which is accurate enough to simulate the tensile test. Now you use the same set of value and now you start giving different deformation paths, okay, to that set of grain. So typically it works like this. So this is actually each of these I would say cube is actually representing one grain, And the orientation of these grains were actually calculated using EBST. Okay, and then micromechanics based model was implemented on the top of that. These are the calibrated coefficient using tensile test. Okay, so only tensile test we did and calibrated the coefficient, and then we took this coefficient and then we started doing the biaxial, plane strain, all sort of deformations. Now this is the validation of such type of an approach with an biaxial experiment. So here what we did is, we did equibiaxial experiment also in this material because we have that facility. And we did this crystal plasticity based simulations, and then we checked whether it is working or not. Okay, and here you can see the match is very good, and this is the experimentally found out yield surface and the validation of that with the different models also. So it was very well represented. And then we used the same to actually do the real life simulation. So what we did is we made a cup, okay, using the same steel for which we actually did all those experiments, and we measured the punch load when we are drawing this cup, and also we measured the earring of this earring height. Okay, so basically the cup height is actually showing the amount of earring happening in this cup. And you can see prediction versus experiment using different models. So one is YLD, actually the Barlat-Till criteria, where all the coefficients were calculated using experiment, means real physical experiment. And this is all the coefficients were calculated using virtual experiment, means crystal plasticity based model, which we had developed in-house. And you can see the prediction is quite good, both for the load as well as for the cup height. So there is hardly any difference. So we are confident that such type of an approach can also be used going forward for the testings, etc. Now, the third category of project where we are actually involved is the new forming technology development. Now, one of the forming process which is already being used by automotive industry is hot stamping. And here what do you do is, you have a boron steel, you do the heating of the steel up to 900, 950 degrees centigrade, you quickly transfer it to the die, do the stamping, keep the die in the closed condition, and do the quenching, die quenching, and then the complete microstructure gets transformed into martensite, and therefore the strength what you get in the final component is about 14 to 1500 megapascal. Okay. This is very well common nowadays, people are using that day in, day out. But one of the problem with that is, right now it's the furnace heating. Okay, and the furnace heating has got certain limitations from the productivity point of view. And also you can't use uncoated boron steel because scale formation will happen, and that scale gets transferred on the die life, etc. becomes an issue. So people generally use aluminum silicon coated steel, and then you don't have that problem of corrosion. To address these two problems, what we did is, we started using fast heating process. And what we are doing is, we are doing electrical resistance heating within this die itself, very rapid heating, and then quick forming. Now when we do that, you can see the comparison. Of course, this is not helping to solve the problem 100%, but almost 90% problem is resolved. So this is the typical furnace heating, uncoated boron steel, vis-a-vis the fast heating process. And you can see the difference in the scale level. Not only that, the production rate here increases by almost 60%. Okay, means the cycle time gets reduced by about 60%. Now this technique we have already proven at the pilot scale right now. We are trying to scale it up. Another area where we are working, which is also pilot scale project right now, is composite metal hybrid forming. Because nowadays, once again, the automotive manufacturing companies are trying to reduce the weight, and there is a limitation, a minimum limitation to which you can actually reduce the thickness. And one of the reason is the stiffness of the component, which is also very, very important at times, actually gets reduced, because you are reducing the thickness, which is actually a thickness and the Young's modulus dependent property. So, okay, I'll just 2-3 minutes. So this is the problems we are trying to solve. Okay, this is also at the pilot scale. This is the last slide I have. This is not something we are working, but this slide I had put up recently in another conference also, just as a kind of a food for thought, because this is a serious threat to the steel industry, stamping industry, if it becomes a kind of a mass scale. So this was actually started by Tesla. It is now in commercial use. Tesla is already having, I think, some 16 giga presses across world, and there are 6-7 different companies, Chinese companies mostly, which have also invested into that. Now the problem is, all of us know that high pressure die casting is not a new process. The only limitation was basically the size of the component and the wall thickness what you could have made, right, earlier. That problem has been solved by making very large presses, which can actually pump in the liquid or molten aluminum at a very high speed also. And so after that problem was solved, basically one Hydra, an Italian company, developed that press. After that, now there are Chinese companies which have actually come up with presses up to 15,000 ton. Okay, and now see, what is the impact of this? Aluminum is expensive, everything. Still the cost of ownership for the auto manufacturer is about 8 to 10% less. And one reason is, if we want to make this and this, okay, using typical stamping route, we need to make at least 70 parts. And to make one part, we need 3.5 operation on an average. So we need almost like 220, 230 dies, 230, 240 operations, so many inventories, etc., and then do the welding of 70 parts. So there is a huge complexity in the whole supply chain. So that complexity is replaced with what? One component, probably 3 operations, right? And that helps reduce the overall cost of ownership, even though aluminum is more expensive. And therefore many people, mainly the new electric vehicle manufacturing companies, they are very much interested into it, they are fast adopting it. Now suppose this becomes mass scale, so the whole sheet metal forming industry is going to be at a serious threat. And not only that, even the steel companies like us, because aluminum will become more prominently used here. So it's a threat for us also. We are very much interested. We do not know what is the solution as of now. But I think the probable solution should be focusing on integration of large number of parts. How to do that, that's something, a research topic. I think this team can also think of maybe giga casting using steel, I don't know. So that could be something like that, or giga forming. Yeah, so something of that sort. So that was my last slide, just a summary, which is self-explanatory. Thank you very much. If there are any questions, etc., I would be happy to take that.
No questions, but to Dr. Ravi Kumar and for your good self, you people approach working in tandem with the ARAI.
ARAI?
Yeah, ARAI. Have you heard of this organization?
Yeah. So we work with ARAI very closely. So we do a lot of experiments.
So are they aware of all this kind of, because they are very much after lightweighting of a car?
Yes. So of course we do work with ARAI. We use their facilities also to do some of the experiment which is not possible at our end. They are aware about some of these development, but I understand that they are more focusing on the material and the component testing than developing new forming solutions, etc. Yeah, but unfortunately we are not working together on development of new technology somehow. Our relationship more or less like testing and material characterizations.
Yeah, I mean, I'm in metallurgy background. A lot of things I'm not much conversant with, but my question is, in all such cases, aluminum is coming up. Do you think that aluminum is, same question, replacing steel as far as carbon footprint is concerned, is it a environmentally feasible solution? Because at one point of time there was a hype in aluminium, Audi 8, Audi 7, and again people reverted into steel. And now all these giga press and upcoming forming processes, they are focusing on aluminium. But considering the energy consumption in aluminium melting.
So I think this is a very relevant question which is also getting debated a lot within the industry. So, but it is also evolving. So just let me try and answer it like this. If you just compare the CO2 footprint in at manufacturing stage, aluminium is certainly not good. Okay, steel is better. But if you look at the vehicle total LCA, the life cycle cost, so a large part of emission is actually during the use phase. So if you use aluminium to reduce the weight and reduce the use phase emission, then overall actually you gain. However, then the next question is, suppose you are now going to be EV, like suppose it's an electric vehicle, so there is no question now of the emissions. Then the question is, what about the electricity? If the electricity is also green, then the aluminium manufacturing also will not have that much CO2 footprint, because now the electricity has become green, and aluminium uses lots of electricity to during the manufacturing stage. So it is evolving. So as on today, aluminium manufacturing it's not. But going forward, if the electricity becomes green and all the vehicles also becomes EV, then once again aluminium may become competitive. Yes. Yes.
Another comment I would like to make, this very question that you asked about the carbon footprint, most of the automotive companies, whether Tesla or whether Volvo actually had made a public statement. See, their cost is higher because in the beginning what they are using are primary alloys. Currently what they use are primary alloys. They are already started working on use of recycled secondary alloys. But they are already, Volvo has already announced that they have succeeded with recycled giga castings.
That is where EBLCB and ULSA have all started at this particular point.
Well, anyway, I'm stimulated with this discussion to make my comment. Only one. The thing is that there are doubts for EV itself. So how long does the EV will continue? The buzzword EV, how long? The experts, they say that it will not continue for more than a decade.
So there is, I agree with you that there is a kind of a split verdict on that. One thing is for sure, before I get into that, one thing is for sure that IC engine is no longer going to continue. That is going to die. Okay, that is not sustainable. There is going to be a clean energy propulsion system in the vehicle. Now whether it will be EV or whether it will be hydrogen fuel cell, that debate is still on. The hydrogen, the availability of the hydrogen and the green hydrogen at a cost is a big challenge as on today. So if that problem is resolved, then the EV perhaps people will not be interested into it. Unless and until some breakthrough also happens in the battery technology. Okay. So it is very uncertain because so there is a popular saying, just let me tell you.
Thank you. Thank you, sir. Do you have anything? Okay. So after lunch, so that 2:30 we can join. What is the town? 2:10. So maybe 2:35 like this.